And again, with things like petastatics, they are critical to the safe operation of the aeroplane. If you cast your mind back to Air France, I think it was flight 447. It was flying from South America back to Paris, and it got lost in the middle of the Atlantic. It took them days to find it. And what had happened with that aircraft was that the pitot heads had frozen up because the heaters in the pitot heads weren't powerful enough. The pitots froze up. The aircraft computers lost all the information that they needed for the aeroplane. So the aeroplane didn't know what it was doing. The crew weren't sure what was happening. And between them, the crew and the aeroplane managed to lose altitude and fly into the sea. It was a totally avoidable accident in hindsight, I suppose. But that was the main cause, was the fact that the pitot heads were iced over. The other thing that people tend to forget, ice will form on the windscreens as well, and on the windows. And if the pilot can't see out, it's not very good for him. It can be a bit, shall we say, disconcerting. So again, we need to provide protection for the transparency so we can see where we're going. So those are some of the effects of icing. And icing in flight, we come across an effect called supercooling. Supercooling, I do apologise because the slide is meant to be a video, but I can't get it to run. So when you get 5 minutes at lunchtime or tea break, just pop onto YouTube and Google supercooling. Supercooling is a phenomenon where water will remain in the liquid condition at temperatures well below freezing. Because it remains in the liquid condition, while it's not being disturbed by anything, it's fine. As soon as that water is disturbed, it will turn to ice. It immediately ices over. So if you can imagine a cloud full of water, and that cloud is sitting there at minus, let's just say -10 for argument's sake. As soon as an aircraft goes through that water, that water will immediately turn to ice, and it's going to ice onto the nearest thing to it, which happens to be the aerofoil that's disturbed it. So we start to get the ice forming on the aircraft. And that ice will build up rapidly. And what we have is a term called the collection efficiency. So as an aerofoil is going through the air, as the water hits it, turns to ice. Depending on the size of the aerofoil, depends how much ice is going to form on it, and that's what's known as our collection efficiency. So if you can imagine a wing of an aeroplane, we've got a big cloud. That wing goes into the cloud. The water that's striking that wing and turning to ice is going to form on the aerofoil, and it's going to build up very, very quickly. And it's that build-up of ice that's known as the collection efficiency. If you think back to your aerodynamics lessons, as the aerofoil is flying through the air, it's sending out these pressure waves in front of it. So that the cloud in front has got an idea that there's something coming. So it won't move out the way, but it gets a warning that the aircraft's coming. So the amount of water, the amount of ice that's going to build up on the leading edge of the aerofoil depends on how thick it is. So if you've got a large wing, you're going to get ice forming. But then if you've got a tailplane, yeah, which is a much smaller leading edge, smaller aerofoil, that pressure wave isn't as large, so we're going to get more ice forming on the leading edge of the smaller aerofoil. So it says in the notes that the wing, the larger aerofoil, has got a collection efficiency of around about 45%, whereas the smaller radius leading edge, something like a stabilizer, that collection efficiency can be up to 95%. So the smaller the aerofoil, the more ice is going to form on it if we fly through this supercooled water. Does that make sense?
Jim, you mean this collection efficiency is indirectly proportional to the surface area?
Yeah.
Indirect.
Yeah. So if you've got a large aerofoil, yeah, as the aerofoil is going through the air, it's sending out a pressure wave in front of it, so that the air in front of the aerofoil is going to move slightly out of the way. So obviously, if that air in front of the aerofoil is full of water, yeah, it's going to move slightly. So you're not going to get as much of a build-up on the aerofoil as you would on a small, sharp radius. Yeah, so your large aerofoil, yeah, will collect a certain amount of ice as it flies through the cloud, but a smaller, sharper aerofoil, such as a stabilizer, yeah, it's going to strike more water and it's going to collect more ice on the front of it. So you get a bigger build-up on a small radius leading edge, yeah, than you will on a large radius leading edge. Does that make sense?
Yeah. Thank you.
Yes.
Makes sense.
Tell me if it doesn't. I'll try and think of a better way of explaining it. Leave that one with me. I'll try and think of a better way to explain it. But for the time being, just trust me. If you've got a large radius leading edge, yeah, it's not going to collect as much ice on it as a small, sharp leading edge radius. Yeah. So the collection efficiency is how much ice is going to build up on that aerofoil, and a large aerofoil is going to have a smaller collection efficiency than a smaller leading edge. Yeah. So your small leading edge, 95% collection efficiency means it's going to get an awful lot of ice forming on it. The large leading edge, not so much. I'm just trying to think of a better way of explaining that, but offhand,
But Jim.
Yeah.
But normally, in common sense, like greater the area, greater will be that contacting area with the supercooled air. It seems a little bit confusion. Like if greater area is exposed to that supercooled air, that the greater chances of being accumulated the ice. Is it? But what causes that? It's inversely proportional with this area. What?
Can you see my picture on the screen?
Yeah.
Right. If you imagine my glasses case is a leading edge, yeah. As that leading edge is traveling through the air, it's sending out a pressure wave in front of it, and that pressure wave is going to warn the air in front, the aerofoil's coming. Yeah, so there's a large pressure wave in front of the aerofoil, so that the air will separate. So there's not as much moisture hitting the large leading edge. If you get a small sharp leading edge, that pressure wave isn't as big, so it's going to meet the airflow, a lot sooner, so that there's going to be more moisture allowed to accumulate on that smaller leading edge.
Okay. It's all about pressure.
Does that make sense? Can we see that?
Yeah.
I'm desperately looking around for something else to show it with, but the smaller and the sharper the leading edge, the more moisture is going to strike it, so the more that moisture is going to build up into ice. With a larger leading edge, it's not going to get as much moisture forming on it or hitting it, because it's getting less moisture hitting it. It's going to get less ice forming on it.
Okay, thank you.
Are you sure?
Yeah.
Pinky promise?
Pinky promising.
Okay, so we've said that the aircraft is going to fly through the air. If it meets icing conditions, ice is going to form on the aerofoils. It's going to form on the windscreens. It's going to form on the pitot heads, and the effects of that ice ruining the lift, increasing the drag, increasing the weight, possible loss of control. And we said that large aerofoils collect less ice than small aerofoils. Yeah, and that ability for the ice to form on it is known as the collection efficiency. So your small, sharper, smaller radius leading edge has a higher collection efficiency than a large leading edge. Wherever we're operating in the world, there are going to be different types of ice we will come across. Yeah, and the ones that we worry about are glaze ice, rime ice, and hoarfrost. Those are the common types of icing that we meet that'll affect our aircraft in flight. There are other types of icing, and they come under the umbrella of mixed ice, I think it is. But the ones that we talk about in the notes: glaze ice, rime ice, and hoarfrost. Yeah. Out of those, glaze ice is the most dangerous. Glaze ice is sometimes called run-back icing, and that occurs in dense clouds, large water particles, and those water particles are sitting there in the liquid form. Yeah, the large drops of rain. Where the leading edge of the aerofoil meets that cloud, that water, as it strikes it, we said that the droplets are going to get agitated, they're going to turn to ice. But if you cast your mind back to yesterday, when we're changing state, there's an awful lot of heat given off without that change in temperature. So what happens? The aerofoil will hit the water in its liquid form, and as that water is turning to ice, a small part of it turns to ice, and as it does, it gives off a lot of latent heat, which keeps the rest of it liquid for a short period of time. That latent heat delays the freezing of the water droplet, and that water will run back over the top of the aerofoil before it finally turns to ice, before it freezes. So we're not just getting ice forming on the leading edge, we're getting the ice forming over the top of the aerofoil as well. I'll just go forward one slide. Yeah. So what's happening? The aerofoil's hitting the water. The water wants to turn to ice instantly. Some of it does, but as it turns to ice, it's giving off that latent heat, and it remains in its liquid form for a little while. So it runs back over the leading edge onto the upper and lower surfaces of the aerofoil. Yeah, it says it builds up very, very rapidly. Yeah, and because it's gone beyond the area of ice protection, it's quite hazardous because we've got no way of getting rid of it then. Yeah, it's the most dangerous form of icing that we talk about. Yeah, like I say, as we're flying through the air, if you can imagine, that's your aerofoil. You've got these large drops of water suspended in the air. As the aircraft strikes them, those water droplets want to turn to ice. Initially, they do, but because during the change of state they're giving off that latent heat, yeah, they remain as water, and because of the airflow pushes that water back over the top of the aerofoil, and as that water moves back, it starts to freeze. But it's freezing beyond the area of the ice protection that we've got fitted to the aircraft, which is what makes it so dangerous. Yeah, and you can see it's really shiny. It forms a very transparent coat of icing. There's no air in there. It adheres to the surface very, very quickly, and away we go. Yeah. Something worth sticking your highlighter through that has cropped up before. When we talk about glaze ice, when we talk about run-back icing, yeah, it's large particles of water, yeah, and it remains in its liquid state from temperatures between 2 degrees to -10, and it's only going to turn into ice once it's been disturbed, once it's been agitated, and that happens by the leading edge traveling through it. Everybody okay with that? Any problems, questions, queries there? No?
No, continue.
No.
Okay, fantastic. That's what we like to hear. Right, so that's your glaze ice, your run-back icing, and run-back icing, the most dangerous type. Another type of icing that we get is what they call mixed ice or glime ice. Yeah, that ice forms when complete freezing of the water particles on impact takes a little bit longer than that of rime ice. So what's happening is the water particles are striking the leading edge. They're remaining as water for a bit longer, but the large and the ice forms fairly rapidly, and we get quite a quick build-up of ice on the leading edge where the water's striking it. Forms when complete freezing of the water particles on impact takes longer than in the case of rime ice. The ice will form when the water particles are large and the air temperature is very low. Remaining water will freeze sufficiently to trap some air, and because you got air trapped, you get this sort of milky appearance in the. It's what they call opaque, sort of milky appearance of the ice. Again, the delay in the freezing of that water gives it time to flow back from the point of impact. Flows back over the leading edge, and the surface is rough, but not as rough as your run-back icing, your glaze icing. Yeah, so it's very similar in effect, in as much as it runs back over the aerofoil, but because it takes a bit longer to freeze, air's trapped in between it, so it becomes easier to spot, should we say, than the run-back icing, which remains transparent. and if you don't know that you're in icing conditions, you look out the window, you can't see that run back icing. It can take you take you by surprise very quickly. Rime ice is another one. Yeah, rime ice, if we've got low temperature air, the cloud particles, the water particles in the clouds are fairly small. The water striking the aircraft, it doesn't spread when it hits it, but it freezes at the point of impact, as it says there on the slide. So that the water droplets are gonna hit the aerofoil, and where they strike the aerofoil, they're just going to freeze straight away. So each water droplet becomes its own individual piece of ice that'll stick to the aircraft, and those particles will build up and build up. Yeah, that ice, because the individual particles building up, that gives a very, very rough surface. So again, because you've got the rough surface, that is going to have a really horrible effect on the airflow over the aerofoil, so you're going to lose your lift. You're certainly going to get a walloping great increase in drag. Your rime ice, because it's got all that air in, it's very, very noticeable, very white, very, very, very chunky. So again, if we're flying in that type of icing, the pilot can look out the window and he'll be able to see, I've got ice formation. Same with his Gleim or his mixed icing. Chances are he's going to be able to see that. He's going to notice that he's got icing. Whereas the run back icing, because it's transparent and because it goes beyond the ice protection measures, that's where it becomes very, very dangerous.
Can you go
dry ice?
mix ice, the Gleim ice once again? The second one.
The Gleim ice. Gleim ice is what they call mixed ice. It's a mixture of rime ice and glaze ice. The mixed icing, it says it's complete freezing of the water particles takes a bit longer than previously mentioned. Yeah, so with your mixed icing, you're having the same effect as your run back. The aerofoil is striking the water particles. The water particles are partially freezing, but because of the latent heat they're giving off, some of that water remains liquid and it flows back over the leading edge of the aerofoil, and it flows back beyond the area that we've got the ice protection measures fitted. With the mixed ice, yeah, that water, when it freezes, it gets air trapped in it. Yeah, and because it gets the air trapped in it, it's more visible. Yeah, we can see it, and although it spreads back over the aerofoil, if somebody's looking out the window, they'll see that ice is forming. With the glaze ice, the run back icing, exactly the same principle applies. The water droplets are hitting the leading edge. The part of that water droplet is freezing, but the rest of it, because of the heat that's given off, is running back over the aerofoil. But because of where it's running back, it's very, very transparent. Yeah, so you can't really see how much of it is forming. Yeah, because it's not having any air trapped in it. So you get this transparent coat, and that run back icing, because the water's flowing over the top, the layers of it build up very, very quickly. Yeah, so it builds up very, very rapidly. It's building up behind the area of ice protection, so it becomes more dangerous than the others. Oh, I've lost my mouse. Where have we gone? You okay with that? Can you say that okay?
Okay.
Okay.
Yes, sir.
Anybody
Okay,
else? All Right. So those are some of the types of ice that we come across. Another potential for ice formation is what they call dry ice. Yeah. Once we get above 40,000 feet, yeah, because it's so cold, we tend not to get water droplets at those altitudes, so that conventional icing doesn't become a problem. But what you can do is get very small crystals of ice forming at those altitudes, and that's known as dry ice. Yeah, and if you get a period of or an area of dry ice that's quite heavy, those little crystals of ice can block up things like pitot heads. Yeah, they can block ducts. So once we're above 40,000 feet, yeah, icing tends not to be a problem, but you can potentially get this dry ice forming. You've probably seen dry ice. They use it in nightclubs and on stages in theatres to give a cloudy effect. That's dry ice. Once we're at lower altitudes, or the aircraft is on the ground, another thing that can form is hoarfrost. And the hoarfrost it's that lovely feathery white ice that you see forming on trees on a cold frosty morning. Yeah, so hoarfrost, it'll form on the surface below the freezing point, surface below 0 degrees. And where we've got water vapor in the air, as soon as that touches a surface that's below 0 degrees, it will turn immediately into ice, and it gives us this lovely white coating. You've probably all seen it. Problem with hoarfrost is if we've got a wing, yeah, that wing's got fuel in it. The wing's cold. As we descend, as we come down from altitude, any condensation that forms on that cold wing surface can turn to frost. So you can get a buildup of frost. It tends to be, I'll say that tongue in cheek, it tends to be more common on the ground where the aircraft's been left out overnight. Yeah, the cold wing surface, the cold fuel in the aircraft, condensation strikes that cold surface, and it starts to solidify, and we get that buildup of frost on the aircraft. Again, another example of hoarfrost starting to build up. Start to get a buildup of ice. You can see the ice forming on the nose of the aircraft, and now we can see it starting to form on the windscreen there. So we're going to get additional problems with icing. So as I was just saying, if an aircraft's coming down through fog, through rain, as it's reducing in altitude, yeah, that wing has been at minus whatever for so long. As it comes down, temperature downstairs warms up, we get condensation forming, and if that wing still retains that low temperature, we can get ice forming on the wing as we're in the descent. Yeah, so again, hopefully you can see it. Yeah, just an example of the ice forming on the upper surface, and it's purely because that wing is so cold. We've come down through rain or fog, bit of condensation, and we can get ice forming on the wing. If you propeller aircraft, if we've got propeller aircraft, ice forming can induce a stall. Yeah, as the aircraft's flying along, flying straight and level, yeah, the ice forming on it is slowing the aircraft up. The propeller's becoming less efficient, so the stall can occur speeds much higher than you'd expect. Yeah, and angles of attack definitely a lot lower than you'd expect the aircraft to be stalling at. Induced stalls because of icing are a fairly common problem, believe it or not. Certainly places like the States where they're out flying in the mountains, in the mountainous regions, if they haven't put the de-icing fluid on the aircraft, fly into icing conditions, that ice, as I say, can gather on the propeller, gather on the wings, and because you're losing your forward airspeed, you don't realise it. The angle of attack's well within what you consider to be the normal limits, but the aircraft can stall. Everybody okay with that? I'll just bear with me 2 minutes. Just make sure I've explained that properly. The effects of the ice formation, the different types of icing. The run back icing, remember that's the most dangerous one. The temperature range, your large water droplets, and they can remain liquid from 2 degrees to minus 10 degrees, and they'll only change to ice once they've been struck by something. And then we looked at the different types of ice. Condensation. Undetected stalling. Stall occurs at speeds much higher than the normal stalling speed. Propeller-driven aircraft more likely to be affected by that. Stalls could occur about 30% above the normal stalling speed. Pilot unaware of the onset, and yeah, we've done that. Happy days. Is everybody okay with what we've covered there thus far? Yeah, excellent. Right, what we'll do, we'll just very quickly state it's worth knowing the difference between anti-icing and de-icing. Anti-icing is the prevention of the formation of ice. Yeah. De-icing is the removal of any ice that's already formed. On our aircraft, we can use our ice protection, depending on the type of system. We can use it as anti-icing, i.e. turn it on before we go flying, and it'll prevent ice from forming on the aircraft. Or we can have a de-icing system where if ice has formed on the aeroplane, we can get rid of it. Yeah. So to that end, there are different types of system that we'll build into the aircraft, our ice protection systems. Yeah, so with our ice protection, there are different ways of protecting the aircraft, protecting the aerofoil. And what we'll do, we're a couple of minutes early. We're about 5 minutes early, but it's a good place to stop and grab a cup of tea, and then we can run through the different types of protection after tea break. Right, has anybody got any questions at all on anything that I've covered this morning so far? Is anybody out there?
No question, sir. It's okay, sir.
Okay.
It's okay.
But
Jim, I have one question.
You have one question, yeah? Go on.
This cap 393 and schedule 4 of the. Hello.
Yeah, Cap 393, that's the air navigation
Hello, Jim, can you-
order.
Hello.
I can't hear you. Is that Prakash trying to talk to me?
Yeah, yes, yes, Jim, can you hear me?
You're very, very broken.
Can you hear me?
I can just, yeah.
Jim, can.
No, you keep dropping out.
This Schedule 4 and Cap 393, these are the same thing? Okay,
Yeah.
we'll talk
Yeah.
later.
Cap 393 is the air navigation order. That's the rules and regulations. And Schedule 4 is the area of those regulations that deal with the protection that we've got to carry. Yeah. So if you remember 393, you won't go far wrong. That's the where all the regulations are contained. Schedule 4 is just the area within that manual.
No, I think Schedule 4 of Cap 393, yeah?
Yeah.
Okay.
You can underline whatever are frequently earlier asked in the exams, because in these notes we have only theories, lots of theories.
Yeah. Right. That Schedule 4 that it talks about is Cap 393. Yeah, just think Cap 393, you won't go wrong. And Cap 393 is the air navigation order. Anybody else got any questions?
No, not questions. Can you underline the frequently asked, some important from exam point of view that I'm asking you?
Well,
In the notes, in our training notes.
yeah. Not really. I mean, we need to know where the regulation comes from, and that's from Cap 393. We need to know what the most dangerous type of icing is, yeah, and why it's dangerous. Need to know how it forms on the aircraft, and we've talked about that. The difference between anti-icing and de-icing. One is preventing ice, the other is getting rid of ice. Yeah. And the effects of icing. Yeah, well, why do we need to get rid of that ice? Why is it dangerous to the aeroplane? And that should be fairly straightforward. If you're going to lose lift, you're going to increase drag, you're going to gain weight, so you're going to lose lift. Okay with that?
Okay, thank you.
Right, what we'll do there, we'll have tea break there, 20 minutes, and we'll come back. Well, it'll be 10:30 my time. I haven't got me. Kathmandu, 15:55. So we'll say 16:15.
16:15, yeah.
Yeah, so that's 20,
Okay.
20 minutes.
Fine.
All right,
Okay,
see you then.
okay.
See you in a minute. Hello?
One thing I want to ask, what about this killer ice formation on aircraft wing upper surface due to cold fuel and precipitation?
What's that?
Yeah.
If you've got the aircraft at altitude, and because the aircraft's at altitude, the surface of the wing is going to get very cold. And as the aircraft descends, as it comes down through cloud, if there's any moisture in that cloud, condensation, if it's foggy, if it's rain, because you've got the cold surface and the rain landing on it, that can form a layer of ice on the wing surface. Yeah?
Yeah. In this case, fuel temperature take it. And this, what about this fuel temperature?
Yeah, well, the fuel in the aircraft, if that's cold fuel, and that can lower the temperature of the wing skin as well. So if you've got cold fuel sitting in there, and again, if you get condensation, that can form ice. Okay with that?
When in flight, in high altitude, what do we do for the fuel not to freeze?
Normally, on a large aircraft, the fuel is heated. To stop it, because don't forget, fuel has got water in it naturally. So what we don't want is that fuel freezing up. So the fuel during flight is heated, but there's just a possibility if the fuel's been sitting in the tank and the wings already cold, if that fuel temperature's dropped a bit, then you can get ice forming on the skin of the wing.
In this case, we have to use some additional things, or we don't?
No, not normally. Not
Okay.
normally.
Okay, thank you. Thank you.
Okay. If the aircraft's been sitting on the ground and it's going to take off, normally it's had de-icing done on it before the aircraft goes flying, so that helps prevent the formation of ice. But it's a potential. It has the potential to be a problem. Right. Anybody else got any questions before we kick on?
What about this in helicopter sense, the anti-icing and de-icing? Any, because I work in helicopter, so.
Yes, you get ice protection on helicopters. Normally at the root of the rotor blade. Okay. You'll get ice protection on the engine intakes if you've got turbine engines. As we'll see in a wee while, we have windscreen protection.
Okay.
I think the others. That's pretty much it, but there is ice protection on helicopters, yes.
Okay. Okay, thank you, Jim.
That's okay. Anybody else? No. Okay then. Right, we'll carry on then. We talked. Sorry.
Excuse me.
Yeah.
What does it mean? Zero fuel, sub-zero fuel.
Below freezing.
Below freezing. Okay.
Just make sure that I'm reading it in the right context. Yeah, below freezing. Okay then. So we've looked at why ice is so dangerous to the aircraft. We've said that there's regulations in CAP 393, which is the Air Navigation Order, the same thing. And those regulations tell us that we need a minimum of ice protection fitted to our aircraft. And the majority of that ice protection is actually part of the design and the build of the aeroplane. We've seen why ice is dangerous and some of the additional effects we can have from icing. So now we need to look at the protection measures that we can put in place. Yeah, and there are different types of protection that we can fit to our aeroplane. Obviously, it's all down to the designer, what we're doing with the aircraft, the size of the aircraft, what we're gonna put on there. On the ground, we can carry out anti-icing and de-icing by spraying the stuff on. That's all Module 7 stuff that we've already. I think you guys have done Module 7, haven't you? I'll take that as a yes.
Yes, sir. Completed, sir.
So excellent. So we've looked at all that, but now we're going from the ground. We're going up into the air. So we need an integral system within the aircraft to protect us from the various elements. Yeah. So there's 4 main methods of ice protection that we're going to use on our aircraft. And the 4 primary methods are what they call thermal ice protection, and that's by using hot air. And we're going to run hot air down the aerofoils. We can have electrical ice protection, which is heater mats, special mats with little heater elements in critical positions that we can turn the electrics on, and that'll heat up. We've got pneumatic ice protection. And the pneumatic ice protection is inflatable, what they call boots, that we fit to the leading edges, and as the boots inflate, they'll break away any ice. And then we've got the chemical method, or sometimes known as the fluid method, and it's sometimes referred to as the wing, where we actually get an anti-icing fluid that we pump out onto the aerofoils of the aircraft. So we'll have a look at those systems in a little bit more depth. Yeah, and with our thermal anti-icing system, yeah, what we're going to do is take hot bleed air from the engines, and we're going to duct that air down the leading edge of the wings and down the leading edge of the fin and the horizontal stabilizer. Because that bleed air is coming from the engines, it's very hot. Yeah, but at the same time as you've got hot air going down the inside, you've got cold ram air flowing over the aircraft, so that gives a level of structural protection. Yeah, air temperature 230 to 250 degrees, it's controlled at. Turn the system on, yeah, and via a shutoff valve, that'll allow that bleed air to flow down into into the system. Yeah. All your anti-icing, de-icing control from the cabin, the system switched on. Yeah, and once we switch the system on, in this case we've got little rear-mounted engines. Yeah, there's a little shut-off valve. The pressure regulator shut-off valve will open. That will allow the hot bleed air then into the system. That hot bleed air is going to flow up to the wings, and we're going to duct that hot air down the leading edge of the wings. At the same time, that hot air is going to be ducted up to the leading edge of the horizontal stabilizer. Yeah. To preserve, or not so much preserve the air, but to make sure that hot air is used efficiently, and that we're not going to affect the performance of the engines, what we do with the thermal system generally is cycle the air between the horizontal stabilizer and the wings. So the wings will de-ice for a wee while. The wings panel shut off, and that will then direct the air down to the horizontal stabilizer. That'll run for, I think it's 2 or 3 minutes, and then the thing will cycle back, and it'll carry on cycling so long as the thermal system is selected on. Yeah, so it's just a typical system. Yeah, shut-off valves. Yeah, tail protection, shut-off valve. Yeah, so that's going to allow us to cycle between the tail and the wing. The wing shut-off valve, again, that's going to open and close. We'll get this cycling. And then we're going to have a pressure transmitter fitted into the ducting, both sets of ducting, just to make sure that there's no blockage or anything, and we're not going to get an overpressure of the duct. If you get an overpressure, obviously you're going to get an over temperature. That could have structural consequences. If you haven't got sufficient pressure, you're not going to get the de-icing effect that you need. Yeah. So how we're going to do this? Yeah, well, like I say, we've got our ducting, and that ducting is going to run down the leading edge of the aerofoil, and we're going to pump hot air into that duct. Along the length of the duct, there are little perforations, yeah, which allow the hot air into the leading edge of the aerofoil. There's a void in the leading edge of the aerofoil where that hot air goes, and that keeps the leading edge nice and warm and toasty. So any moisture that hits it, because it's warm, it's not going to freeze. It'll just carry on. The other thing as well, obviously, if we do get ice forming, we turn the system on. Because we're warming up the skin, it's going to melt any ice that forms, and that's going to be carried away by the airflow in the form of moisture. Yeah. That air obviously needs somewhere to relieve to, otherwise pressure would just build up. So it gets ducted again into the void behind the leading edge in front of the spar, and then it's allowed to escape to atmosphere. The beauty of the thermal system, allowing the air into that void, yeah, it gives us a good area of protection for the prevention of that ice building up. Yeah. Obviously, with a larger aircraft, we're going to have leading edge devices fitted, and we need to make allowance for the movement of those leading edge devices. The way they get around that with the slats is they just have telescopic pipe work. Yeah, but just car aerial, just a sliding tube. Yeah, so the main duct runs down the leading edge of the wing, and then you've got this telescopic duct to the spray tube that's fitted in the extreme leading edge. Yeah, we call it a spray tube, sometimes referred to as a piccolo tube, because it resembles because of the little holes, it resembles a musical instrument. So if you hear the term piccolo tube, yeah, it's just a perforated tube. So yeah, your piccolo tubes like that, and it's just got little holes in. Forget those holes. So yeah, it's just got little holes in, and the hot air's blown out through those little holes onto the leading edge. Yeah. So again, hot air from the tube into the between the layers of skin on the leading edge, gets ducted through there, comes back into the wee void just behind, and dumped off out to atmosphere. Yeah, when the slat's retracted, obviously the telescopic part of the pipe just retracts into itself, and again everything happy. Okay with that? In the notes, it goes into the internal workings of the pressure regulator shutoff valve. We don't really need to concern ourselves too much with that. Excuse me 1 second, I've just got a delivery driver pitched up. Hiya. Can you just dump it in the front porch for me, please? Thanks. I'm sorry, I'm in the middle of teaching. The name's Campbell for your thing. All right. Cheers, buddy. Lou, that's just my beer. He's just put it in the porch. Can you just drop it by the cloak cupboard? Ta. Sorry about that. That was my urgent delivery of beer to keep me going during the UK lockdown. Unfortunately, it's not Gurkha beer.
Okay, sir, no problem.
Yeah. We like the Gurkha beer.
If you want, we can send it from here.
Yeah. Yeah, I did try Nepal Ice the last time I was out there, but by heck, that's strong. that made my legs go wobbly.
Tuborg is good.
Which one?
Tuborg.
Tuborg, right. Yeah. No, I like the Nepalese beer. It was lovely. Yeah.
Strong one.
Yeah, very strong. Yeah. Yeah, but yeah, Gurkha beer I think was my favourite. Right. Anyhow, that's that's my emergency supply just been delivered. So sorry about that. Sorry for the interruption. What we're doing? Anti-icing. Yeah. In the notes, it talks about the internal workings of the shutoff valve. We don't really need to get involved for exam purposes, wondering how the thing's going to work. But what we do need to know is that the system cycles itself between the wing and the tail of the aeroplane, and it does that by a timer, and the timer sends a signal to a solenoid valve, and that solenoid valve will open and close. As the solenoid opens and closes, it allows hot bleed air into the particular duct. So in this case, let's say this is the wing valve, the pressure regulator shut-off valve. Yeah, when we're ready to go, yeah, the system will send a signal to the solenoid. The solenoid will open. That'll allow air to flow through the leading edge ducting. After a period of time, the timer will click out. The solenoid will operate, and it will shut off the supply to the wing anti-icing. At the same time, for the tail anti-icing, as the wing one shuts off, the tail valve will open, and again that will allow air to flow through to the tail, and it will heat the leading edge of the tailplane for I think it says 3 minutes in the notes. I'll have a look and check in a moment. And that cycling will continue, yeah, until the system's switched off. Just bear with me 1 second. I don't want to give anybody bad information.
Is it 2.5 minutes?
2.5 minutes, yeah.
Page number 12.
Yeah, bingo. Thank you. So I don't want to give anybody bad information, but as far as we're concerned, we need to know that the system cycles between the tail and the main wings. There's a indicator that tells us which part of the system's in operation. Wing de-icing light will go off, the tail de-icing light will come on, so the crew will have a look at that, and they'll know which particular part of the cycle that they're into. There is a test facility for on the ground. Obviously, you know, it's a system. It's going to be using hot air, and we're going to have to check that system periodically on the ground. So there is a facility for testing, but during the ground test, the temperature that we allow into the leading edge is limited to, I think it's 90 degrees. Yeah, a little overheat protection circuit limits the temperature on the ground to 90 degrees, and that's there to protect the structure, because during flight you've got the cold ram air flowing over the aerofoil. The temperature that we're pushing down doesn't really matter. On the ground you haven't got that cooling effect from the ram air, so we need to limit the temperature that we put into the duct. Yeah, so that's your thermal system pretty much. Yeah. Again, where you've got Kruger flaps, the Kruger and leading edge flaps. Again, we just need to make sure that we have those protected as well. And so once more, with our ice protection, we can run a bit of ducting down into the leading edge flap or the Kruger flap, whatever it might be. And again, that's just making sure that we've got that, pardon me, level of protection there. Exactly the same sort of principle, the piccolo tube, blowing hot air into the leading edge, yeah, circulating that hot air around and allowing it to vent off to atmosphere. Dead easy. Easy peasy lemon squeezy. And again, just another schematic for the youngsters. Yeah, turn the system on. Yeah. The anti-icing valve will open. That's going to allow hot air from the engines to run down the ducting in the leading edge, heat the leading edge up, And away we go. Tail as well. Yeah, there'll be another valve off to the tail. You'll notice we've got the wing anti-icing. In this particular instance, it runs the WOW switches, the weight on wheel switches, the air ground logic. Yeah. Again, as a protection measure, where when the aircraft's on the ground, if we haven't got the overheat protection, yeah, we don't really want the anti-icing running on the ground, so we can route it through the WOW switches. Again, that tends to be more aircraft specific, but just be aware that the facility is there for it. Old style control panel, yeah, just showing the indicators, yeah, whether the valve position, whether it's open or closed, right and left hand wing, engine that's feeding it. Test facility, whether it's in the automatic or the manual. Pilot can select automatic on subsystems and it'll just look after itself. Other systems, he's got the option of using the thing manually, or if you get a fail in the auto system, we can use manual reversion if necessary. And that was about it for thermal ice protection. Has anybody got any questions there? No. Sound. So yeah.
Like the wing and the tail, these works in opposite fashion.
Yeah. So while the wings got the ice protection selected, while the wings got hot air going through, the tail is closed off. Then after 2.5 minutes, they'll swap over. So the wing anti-icing will shut off and the tail anti-icing will switch on. Another 2.5 minutes and they'll change over again.
This is automatic, right?
Yes, it's all done off a timer. Yeah.
Basically a sequencing mechanism.
Yes, yeah, that's it, exactly.
Yeah.
Got it. Thank you.
Okay, anybody else? Okay.
On ground.
Sorry?
Yeah, on ground, the wing anti-icing valve is closed by ground logic or WOW.
Yeah. Again, that can be aircraft specific, but generally your anti-icing is going to work through the weight on wheel switches, because what you don't want is that system turned on the ground and pushing 250 degrees C air down the leading edge, because that could damage the structure. Yeah. Once we're in the air, we've got the cooling effect of the ram air flowing over it, so that's protecting the structure.
Thank you.
Okay. Anybody else?
Yes, Jim. In the textbook, it has been written the pressure also. Is it worth remembering the pressure because it depends upon the aircraft to aircraft?
It does, yeah. Okay. Yeah. It works at around about 20 psi, but that's going to vary from aeroplane to aeroplane. So, no, I wouldn't worry too much about that.
Okay, thank you, Jim.
Okay.
Yeah.
Yeah, like as I said before, the internal workings of the valve, don't worry about that. Just know that it works on the timer. It cycles between the two. Whichever system's switched on at the time, there's a light so that the crew know whether it's the wings or the tail that's in the middle of its anti-icing. And that the there's temperature is limited to 90 degrees C on the ground when we're doing ground testing. Yeah, and again, that's just to protect the structure. All okay with that? Barrow. The electrical system, and the electrical system gets used on a wide variety of aeroplanes. And the electrical system is a series of heater mats that are bonded to the leading edges of the aerofoil. Yeah. Specially maintained or specially manufactured. The mats come in sections. They're bonded to the leading edge, and within these mats there are electrical elements. We turn the system on. The electrical elements heat up, and that prevents ice from forming. Again, we can use it as a de-icing measure. If we find that we've got ice forming, we can turn the thing on and get rid of it. That said, generally, before an aircraft goes flying, they will turn on the anti-icing system so that they don't have to worry about it. It's switched on. It'll just run itself. So if we do go into ice formation, the mats are already nice and toasty, so nothing's gonna form. Because these things are taking quite a lot of power because they're generating heat, what we need to do is to try and limit the amount of electricity they're using. So the way the mats are run is certain areas will be continuously heated and other areas will be intermittently heated, so that the extreme leading edge of our aerofoil is going to be continuously heated, so there's nothing going to form on the immediate leading edge. The areas between the different sections, again, are continuously heated, just to make sure that each of the separate areas is kept as a separate area. And then the different areas will be heated intermittently. So the heating will come on, it'll run for a period of time, can't remember what it is, and then it'll go off. That'll give time for ice to start to form. The heater will come back on and melt it away. And the other reason for having small areas of heat is we don't want huge chunks of ice forming. Yeah, if we have small areas, it's a lot easier to get rid of the ice in small chunks than it is allowing it to form in big areas. I'm going to take an awful lot more heat to get rid of it. And large chunks of ice, if they break away, go thumping down the airframe, it's going to cause damage to the aircraft. Yeah, so example of a heater mat underneath. Yeah, just little heater elements that run down. It's not a brilliant picture, actually. I've got a better one a bit further along. But that's the idea of the heater mat, little sections that'll heat up. The heating done by electrical wiring built into the mat, and that, like I say, just raises the temperature, keeps the leading edge nice and warm. That is the sort of area where you're gonna find your heater mats around intakes, round critical ducting. Yeah, and the mat itself is made up of various layers. These heater mats are often referred to as spray mats. Yeah, mainly because of the method of construction. But you generally find them called spray mats, and they're made up in layers, and embedded in the middle of the layers are these heating elements, as you can see, the little elements that are heated up, taken from the main electrical supply, so that they're permanently wired into position. Nightmare for the B2s. Yeah, if anything goes wrong in there. Sympathy, none at all. Ha ha ha, B2s. The outer edge, the black coating over the top, is an erosion-resistant coating. It's a sort of rubberized material, and that's there to protect against rain and hail, and just stops the elements getting into the heater mat. What I would say, if you've got these things fitted, is because the outer coating is designed to protect the heater elements, it does get damaged, and if we allow that damage to increase too much, then the actual mat is exposed to the rain and the hail, and that leads to all sorts of problems. So that in the aircraft manual, there are specific repair schemes for recoating the outer layer of the spray mats. Yeah, if you've got the authority to do it, if you've got the permission, if it tells you to in the manual, yeah, just follow the manual and make sure that these leading edges are outer coverings, I should say, are restored properly. We used to have a big problem on the aircraft I worked on. The guys were very, very lazy, or some of the guys were very lazy. And what they used to do, if the outer coating was chipped at all, they'd just colour it in with a black felt tip pen. Nobody could see that there was damage there, and eventually what happened is the rain and the moisture got in behind the adhesive for the spray mat, and the whole section came away, and it created an awful lot of work and an awful lot of problems, whereas for the sake of 10 minutes repairing it properly, we could have saved ourselves an awful lot of trouble. So watch for that one. If you do get damage to that outer coating, yeah, moisture can get in behind. It can destroy the adhesive, and the whole spray mat can part company with the aeroplane, and that's not good news. Heater mats, yeah.
This is also continuously done, or it is how it is working, this electrical?
Yeah, what it is, the heater mat is wired into the main electrical system. Yeah, and we've got these little heater elements that are either permanently or intermittently heated, and that heating is going to warm the leading edge up and either prevent ice forming, or it's going to melt any ice that has formed.
This is continuous or like cycling, like earlier thermal anti-icing?
What happens is, yeah, we'll take the tailplane, for example.
Okay.
The tailplane has got, well, in this case, 4 mats fitted on the leading edge. Those are separate areas, yeah? The extreme leading edge, the black bit down the front, is permanently heated. That's continuously heated. There is always heating going down there. Between the different sections, yeah, there's heating as well. And the area between the different sections is permanently heated. The main surface, yeah, is intermittently heated. So the main surface will warm up for, I can't remember the time, so let's say 5 minutes, and then we'll allow it to cool off. Yeah. So some areas are permanent, some areas are intermittent. But if the question was, do they cycle between the wing and the tail? The answer is no. We turn the heating system on, Yeah, and the heating mats are wing and tail are heated together at the same time.
Okay, I understand now. Thanks.
Is that okay for you, Krishna?
Yes, sir.
Okay.
Mr.
Anybody else while I'm there?
William,
Yes, sir.
so here is written in the notes that the anti-icing mats are supplied continuously with the electricity, while the
Yeah.
de-icing mat is intermittently heated, sir. Means the anti-ice is continuously and the de-icing with the intermittently, sir.
Hang on a minute.
Page number 21, sir.
Page
Yeah.
21, yeah.
Yeah. Yeah, the spray mats, used for anti-icing and de-icing. Yeah, so we can prevent ice from forming, or we can get rid of ice that has formed. Anti-icing supplied continuously with electricity, while the de-icing mat is intermittently heated. Yeah, it's the extreme leading edges that are heated continuously. Yeah, the system we had, it was as I described, but we'll go with what it says in the book, that if we're using it for the anti-icing, yeah,
Yes.
we're gonna have heat there all the time to prevent the ice from forming. If we're using it for de-icing, what we're doing with de-icing, we're allowing ice to form and then we're getting rid of it. Yeah.
Yes, sir. Yes, sir. Clear, sir. Okay, sir.
Is that okay?
Okay, sir. Clear, sir.
Okay.
Mr. James,
Anybody else? Yeah.
Actually in our aircraft we have a de-icing boot, yeah?
Yeah, I'm going to come on to those in a minute.
Okay.
Yeah, we'll look at boots in a moment. Anybody else got any questions there? All right. Yeah, so heater mats. Yeah, so anti-icing, de-icing. Anti-icing, you can have a flow through there, keep them warm. De-icing, they'll cycle, they'll run intermittently. Because obviously de-icing, we don't need all that power being absorbed. Maintenance, yeah, we've mentioned the maintenance on them. The makeup of the mats, how they are built up. Yeah, and the mats used in various places, various positions on the aircraft. With our helicopters, with our propeller-driven aircraft, you'll often find the heater mats at the root of the rotor or the root of the blade. Reason we don't have it right the way down the leading edge is because centrifugal force will, as the rotors are running or the propellers running, that's going to prevent ice from forming towards the outer edges. Maintenance of these things is very, very limited. There's not a lot we can do to them apart from inspect them, make sure that the outer protective coat is undamaged. Yeah, and if we do get damaged mats, then we've got to replace them. Yeah, but that gives you an idea of what they're about. Yeah, the heating element running down, protective coating, and they form part of the aerofoil. Everybody okay with that? Any questions? Any queries there?
Yes, Jim.
Yeah.
This is typical fairing leading edge. Do we need to go in details?
Say that again, sorry.
Typical fairing leading edge. because in the textbook there is a figure showing the details. Do we need to go in details? Do we need worth remembering it? Page number 24.
I'm not sure which bit you're looking at. Page 24. We're looking at the construction of the heater mats, yeah?
No, the construction of heating mat, I understand. The below one, the cable. Insulation bush, cable soldering to heater element, bush bar.
No.
Fang leading connection.
No, all that is it's just showing you how it's connected into the electrical system. You don't need to know that. We just need to know it's part of the, it runs from the electrical system.
Okay,
we don't need to know how it's connected in.
Thank you, Jim.
Okay.
Yeah.
Anybody else? Right, what we'll do, that's I'm at that 11:15 my time. We'll just have 10-minute break, just to stretch your legs, get your eyes, and then we'll finish off these systems up to lunchtime.
Okay, Jim.
Yeah, but we just need to stretch our legs, stretch our eyes away from the screen. So 10 minutes.
Okay.
Okay. Hello. There's another parcel due in the next hour. So if the dog's bark, just go at the door. Cheers. That's that parcel, Lou.
Another carrot of beer.
No, it's medicine for my dog.
All right.
All right. Yeah, I've got 2 dogs, and the old one needs a regular medicine, so that's that just been delivered.
All right.
Okay. Everybody back?
Yes, Sim.
Brilliant. Anybody got any questions on any of that little lot? The only bit I didn't mention was the controllers. Yeah, the system's got a controller, and the controller is divided into 2 sections. One will do the permanent heating, the other will do the intermittent heating, and they'll monitor the correct temperature, and if there's an overheat, the system will trip off. And that was about it for the electrical mats. The next system, somebody already mentioned it, so you guys should be kind of familiar with, is the inflatable boots. The inflatable boots on the aircraft are what they do, yeah. And what we're going to do is to inflate and deflate the leading edge of the aerofoil, yeah. Pardon me. The idea behind it, the boot, a rubber boot with a series of tubes in it, and the little tubes within the boot we supply with air. As the little tubes inflate, yeah, they break off any ice that might have formed on the leading edge. So in this particular case, the three little tubes are inflated sequentially. So initially, the extreme leading edge tube will inflate, and that will break away the bond that's formed between the ice and the leading edge. As that extreme leading edge one deflates, the two others inflate, and what they're doing is they're completely breaking the bond of the ice and making sure that it's carried away in the airflow. Yeah, so these little tubes, normally they are held deflated. We'll come on to that in a moment. If we get ice forming, we turn the system on. The tubes will inflate. As I say, in this case, it's just the leading edge one inflates first. That breaks the initial bond between the ice and the aerofoil. Then the other two inflate and they break the ice away totally, and those chunks of ice are going to get carried away in the airflow. Yeah, the tubes themselves can run either cord-wise or span-wise down the leading edge. It depends on the makeup. The ones that I've come across all run span-wise. Just a series of avenues for air to go down. Yeah, and as we push air in, pretty much the same as we saw before. These things are going to inflate. They're going to break the bond of the ice, and then they're going to push the ice away into the airflow. Some will inflate altogether. Others will inflate sequentially. It just depends on the makeup of the aircraft. I don't know what what your method is, whether they all work together. Certainly on our jet stream they do. Yeah. Span-wise or cord-wise, yeah, that's the cord-wise section. But they're having exactly the same effect. They're breaking the bond of the ice and shoveling it away from the aircraft. So I'm just checking to make sure that I've not missed anything vital there. I don't think I have. No. Right, so boots. Yeah, so where we're going to put these things, on the leading edge of the wings, leading edge of the tailplane, and possibly up there, as in this case, the leading edge of the fin. Yeah, all work on the same principle. Yeah, what we've got is an air supply, normally taken from the engine. Yeah. When we switch the system on, that air supply will inflate the boots. Because you are, in fact, I'll skip on the next slide here. That'll explain it a bit better. As the boots inflate, they're causing this rippling effect. Obviously, we want to get rid of the ice. We want to break the ice away from the leading edge. Yeah, but that is then going to disrupt any airflow going over the edge of the wing. So what we want to do when the boot's not in use, we want to pull the inflated tube back into a nice smooth aerodynamic shape. So the inflation, yeah, the thing will inflate, and then to deflate it, we're going to use some form of vacuum pump to make sure that the air's sucked out and that the tubes go down to the proper deflated state. Yeah. So the thing's going to cycle, it'll inflate, it'll get rid of the ice, and then it'll deflate, and a vacuum pump will bring it back to, as I say, the aerodynamic shape that we need. Yeah. For your controls then, yeah, you've got a control panel where you're going to turn your icing on or your anti-icing, de-icing system on. Yeah, depending on the level of icing, we can select light or heavy selection. Yeah. Automatic modes of operation, yeah, depending on whether the severity of the icing. Indication, yeah, if we've got a light on, fault in the system. Yeah. On off, yeah, manual toggle switch, it says there. Yeah, position 1, all the solenoids energized. Position 2, the B solenoids are energized, so we've got alternates there. What we are interested in though is the pressure that's going into the system. Yeah, so again, there's a low pressure light. So if the system's switched off, we're going to get a low pressure indication. If we've got a leak in the system, again, we'll get that low pressure indication, so we know we've got a fault there. Again, just another example of a control panel for our anti-icing. This one was the wing anti-icing, engine anti-icing for your engine cowlings, all the different probes that we've got fitted to the aeroplane. Your windscreen heaters, we'll look at those a bit later on, and our overheat warning. If we do get an overheat in any of the systems, we're going to get that warning there as well. Yeah, so just an idea of the control panel. Like I said right at the beginning, though, we want to make life simple. Yeah, just turn the system on, yeah, and it'll look after itself. We don't want the crew having to worry about it too much. Right. We don't, again, need to know about the ins and outs of the workings of the ejector valves and that, but suffice to say that the ejector valve is there to make sure that the boot is fully deflated when the system is either switched off or it's in the deflated side of its cycle. So a little solenoid operating a poppet valve. In this case, it's in the ejector flow control valve. Solenoid's de-energized. Valve's de-energized. This pins up, yeah, and the bleed air's shut off. Slight trickle through to an ejector. That's going to make sure that the air from the boot is pulled back, and it's going to get dumped off. Yeah, so the air will be exhausted overboard, I should say. Yeah, switch the thing on. Yeah, the solenoid will energize, push down on the poppet valve, and again, that's going to allow bleed air to flow straight off to the boot to inflate the boot. switch the thing off. Yeah, valve closes. Yeah, bleed air can't go through. Air coming back from the boot, yeah, is caused to go up through the. It's basically a little venturi, but it's going to get dumped off to overboard. Yeah, and that's going to make sure that the boot is fully deflated, which is quite important for our aerodynamics of the aeroplane. Anything I need to say there? Not really. Some of you guys operate the jet stream, is that right? Got the jet streams? Anybody on the jet stream side of things? No? ATRs?
Yes, there are, I think, Buddha, Yeti, both ATR. Lots of guys, maybe.
Right, so you'll know about the pneumatic boots then. Yeah, they are very, very effective, very efficient, very good at getting rid of ice. But we use them as a de-icing measure. So any ice that's formed, we can inflate the boots. We can break that away. Depending on the size of the aircraft, it depends on how many of these boots that you're going to have fitted. Yeah. Again, it's this particular instance. I think it's taken from the notes again. It's just showing the boots operating in little groups. Yeah. Group will inflate, break off the ice, away it'll go, and then it'll deflate. Same up on the tailplane. Anything else we need to worry about in there? No, we need to know that the boots are going to be deflated by a vacuum pump when they're not in operation to maintain the aerodynamic smoothness. There's pressure switch in there to warn us if we get low pressure. Anything else? And it's in there that there's a little water separator. Obviously, we're inflating, we're using air. We might get moisture in there. Last thing we want is the system freezing up, so there'll be a water separator in the system. Pressure regulator, just to make sure that we're not going to overpressurize the boots. Not create any damage there. Again, just let me check, make sure I haven't missed anything there.
Jim.
Yeah.
Can you explain the previous sentence, like vacuum using pump? We have to create vacuum while not in use.
Say that again, sorry.
When boot not in use, we have to create a vacuum by using pump, you're saying?
Yeah, the vacuum pump. Yeah, okay. That slide I showed you a second ago. Yeah, this solenoid valve is what is allowing air to go to the boot to inflate it. So as the valve opens, you've got bleed air flowing straight down to the boot, and the boot's going to inflate, and it's going to break the ice away. That cycle, yeah, as soon as the ice has gone, has broken away, we need to bring the boot back down to deflated. So what happens, the solenoid turns off. It does if I turn the right slide. Solenoid turns off, the valve closes, and that stops the bleed air going to the boot. The air coming back from the boot, yeah, is directed up through an ejector. That ejector is just a little venturi valve, or venturi, I should say. So as the air comes back, it's being sucked out and it's being vented overboard. So now all the air that was used to inflate the boot is being sucked out. Yeah. Turn the valve on, solenoid valve on. Yeah, lifts the poppet, and that allows bleed air to go straight through to inflate the boot again. Yeah, turn it off. The bleed air is shut off, and then the air that's coming back is thrown overboard. Okay with that?
Hello, Jim.
Hello.
I can see that bleed air is going to ejector.
Yeah.
So is this that the bleed air going through the ejector creates that Venturi force?
Yeah. It's all the ejector is a little Venturi. Yes. So when the solenoid's switched off, you're going to get a tiny bit of bleed air blowing across the blowing through this Venturi. Yeah.
Yes.
That is going to pull all the air from the boot. Yeah, because you got that low pressure drop, it's going to pull this air in, and then it's just going to go straight overboard out to atmosphere.
Okay, that is when the boots are required to be deflated. But when the boots are required to be inflated, in that case also the pressure.
The solenoid switches on.
Yes.
Yeah, because but you've got all that air flowing through to the boot. The volume of air that's going to the boot. Yeah, that ejector has got nothing to work with. Yeah, so that the air is all going in the one direction.
Okay. Good.
So you mean to say that to keep the boot in its original condition without air, the ejector function out here, right?
Yeah. When we want to put air into the boot, yeah, the solenoid will energize. It'll open the valve, and it'll allow bleed air from the bleed air source, the engine or wherever, straight through to the boot.
Yeah.
Once the ice has been broken away, we want that boot to deflate. Yeah. So solenoid de-energizes. This poppet valve closes off. There's a small amount of bleed air feeds up to the ejector, and the ejector is just a Venturi basically. Yeah. So as your little bit of bleed air is coming in there, it's causing a pressure drop in the Venturi, and because you've got that low pressure in the Venturi, it's pulling the air back from the boot and sending it overboard. So now that air coming back from the boot, yeah, is being pulled back by the air flowing through this little Venturi. You see that?
Yeah.
So when we call it the ejector, you know, it's just a little Venturi, and all it is doing is pulling air back as you put high pressure bleed air through the Venturi. It causes a pressure drop, and obviously nature wants to fill that void, so it pulls the air back from the boot, and that air back from the boot just goes straight to atmosphere. I think that's covered everything that way on. Yeah, control indication. We saw the panel. If there's a system failure, we'll get a warning light in the cabin. We'll get the attention getters going to tell us that we've got a failure in the de-icing. System switched on. The boots will inflate and deflate in a set sequence. It does give you times there, but that varies from aeroplane to aeroplane. It depends on the level of icing that we've got as well. Yeah. Normally inflate for about 6 seconds, and the period between inflation varies whether it's light or heavy icing. Yeah, if the automatic side of the system fails, there is a manual reversion that we can use. Not a lot else there to say. Maintenance of the system. Does anybody recognise that?
Lukla Airport.
Lukla.
World's most dangerous airport.
So I've heard, yeah. So next time I come out there, we'll have you guys can take me for a trip. Yeah, we'll go and see it. Not.
It's a
pleasure
to take.
Of course, Jim, why not?
I'm terrified of flying. You won't get me in there.
Yeah.
Yeah, it looks nice. It looks interesting. Right. Next bit then, for our boots, carrying out maintenance on the boots, what we're looking at. We've got to make sure that the external surface of the boot is well protected. So there's special polishes, proprietary polishes you can use just to maintain the flexibility of the thing. If we didn't maintain that flexibility, it'd start cracking, and it's quite horrible. If we do get damage to the boot, again, we need to refer to the repair manual. But a lot of the boots you can repair using patches, just like you would with a bicycle tyre. We can stick a little patch over the top and then leak check the thing to make sure that it's holding the required amount of pressure. You're limited to the amount of repairs you can carry out, but again, that's going to be in the SRM, in the manual, and the areas where damage is permissible. Again, the manual. So you can see from that, each set of boots is particular to an aircraft, and the repair limits will be particular to that aircraft. So don't get too bogged down in looking at the maintenance. Yeah, we're just going to make sure that they're kept in good condition, kept neat, tidy, cleaned off. And that was about it. It goes through a typical repair procedure, round about page 40, 45, I think, in your notes. Don't worry about that, because the repairs, you're going to follow the SRM. So all we need to know is that you've got to carry out the repair in accordance with the manual, that you're limited to the amount of repairs that you can apply. The boots need to be polished every so often, just to make sure that they maintain the good conditioning, and the functioning of the boots is carried out again when the manual calls for it, or if we've changed anything. Yeah. System has got to be tested to make sure that the boots are inflating properly, but more importantly, deflating properly, because obviously when they're deflated, they're forming part of the leading edge of the aerofoil, and we don't want any disruption to the airflow. Ta-da! And that was thermal systems. Yeah, not a great deal to them. Fairly simple, fairly straightforward. Anybody got any questions on the thermal side of things? Thermal? Pneumatic, I should have said. See, nobody was listening for my mistake. Okay, then.
We were listening, but we don't want to comment on that.
Hello, Jim.
That's fine. I've just got to make sure that everybody's okay. Nobody's got any
Don't you-
questions.
Not yet. I think.
Hello, Jim.
Yeah.
For the exam point of view, we have to memorize this ejector flow control valve solenoid energized and de-energized.
No. No, you just need to know that ejector valve is making sure that the boots are deflating, that it's creating a vacuum, it's sucking all the air back out the boots. That's all you need to know.
Okay. Thank you.
Right. Ta-da. The next system we've got is what they call the fluid system, sometimes called the chemical system, sometimes known as the weeping wing system. Yeah, and what we're doing with this is we are allowing a de-icing fluid to ooze out of the leading edge of the wing, and it's going to break the bond of any ice that's formed on the wing. It's going to get under the ice, going to break the bond. We can also use it as an anti-icing system. So prior flying into icing conditions, we can again put this anti-icing fluid onto the wing so that any ice that might be around isn't going to form. The fluid system is very, very common, and it is very good, very efficient. Has certain advantages over the other systems in as much as it doesn't need a lot of electrical power, unlike the mats. Yeah, we're not drawing off electrical power. It doesn't use bleed air from the engines in any quantity. Yeah, it's apart from the fluid that we're going to use, it's very light. The components are very light. The pipe work is very light. Yeah. The leading edge, as we'll see in a minute, is porous, and what we're going to do is squeeze fluid out through the leading edge. Yeah, and because it's part of the leading edge, we can have it as a stainless steel or a titanium material, so it's quite resistant to damage, unlike the electrical mats and the boots. Yeah, where they can get damaged by rain, hail, small children, stones, that sort of thing. With this, because you've got a metal leading edge, it's a lot more robust. Unlike the boots, yeah, we're not got any inflation, deflation, so we're not disrupting the shape of the leading edge. The fluid that we squeeze out is going to run back because the airflow is going to carry that fluid back. So it's going to give protection behind the leading edge as well. So with our run back ice, we saw that flowing back over the top of the wing. Yeah, same sort of thing's going to happen. The airflow is going to carry the de-icing fluid back over the wing and give another layer of protection. If we're not using it, system switched off. Yeah, if we're flying to ice, we can turn it on. So we're going to preserve the chemical that we need, the fluid. So we've got good length of time for our protection. Yeah, and again, with the system, it's getting rid of the ice. The pilot doesn't need to know how much ice he's got on, whether to turn the system on or not. Yeah, it'll just get rid of it. So what have we got then in our chemical system? We're going to have a reservoir that's filled with the anti-icing, de-icing fluid. Yeah, there's going to be a pump or a couple of pumps to push that fluid down to the leading edges where it's needed. Yeah. In this case, you can see we've got two pumps. We've also got an interconnection between two systems. So if we get a failure in one pump, we can use the other to carry on with the system. From there, we're going to go down to either the tail or the leading edge. We'll go with the leading edge. And we're going to come down to what they call a proportioning unit. And the proportioning unit is just there to make sure that each distributor gets the right amount of fluid. Yeah, because obviously some panels are bigger than others. We need to make sure that they all get their correct quantity at the correct time. So the proportioning unit's there to do that. Pressure switch just to make sure that the fluid is getting fed down to the system at the right pressure. If it isn't, it'll put a warning light on in the cab. Ta-da! Yeah, so the components that we're going to have in the system. Yeah, let's say we had a little reservoir. We're going to have our pump. We're going to have the proportioning unit. Yeah, and that's the thing that's going to take in the fluid, and then it's going to send it to the individual distributor panels. And these are the distributor panels. The distributor panel is the leading edge of the wing. And the leading edge of the wing has got millions of little holes drilled into it. So what we do is from the proportioning unit, anti-icing fluid is going to be pushed down to the leading edge of the wing, and it's going to go into a void between the wing skin. Yeah, these voids, yeah, lots of little holes in there. So as we squirt fluid into the leading edge, it's going to come out through the holes, yeah, and distribute the de-icing fluid right the way across the leading edge of the wing, the distributor panel. Yeah, once that fluid has been released, any ice that has formed on the wing, that fluid is going to break the bond underneath it. The ice will break away, and away we go. If we want to use it as an anti-icing measure, we can squirt some out. The airflow will naturally spread it over the leading edge, and of course, any moisture that comes into contact can't form ice. Okay with that? Yeah. So yeah, just this porous plastic. Again, that's just a lining for the steel. The plastic allows the fluid to go through. Yeah. And again, it weeps out the leading edge, and the airflow will carry it around, give it good protection. Yeah. Our portioning unit. Yeah. We've got the main supply in from the pump, from the reservoir, pumped down to the proportioning unit. And what happens, the metering plug there is just making sure that the fluid is distributed to each of the outlets in the correct quantity. Yeah. From there, as the fluid goes through the metering plug, yeah, it's directed to its particular outlet. Each outlet got its own little non-return valve fitted to it, check valve. So if I'm pushing fluid out of this particular outlet, yeah, I don't want it going into that one or into that one. So each outlet's got its own little NRV fitted. So that just makes sure that each section is getting the right amount of fluid directed to it. Yeah.
So this works in both anti-icing and de-icing?
Yes.
Okay.
Yeah, normally you'll use it as a de-icer, but you can use it as an anti-icer.
Okay.
If you know that you're going to fly into icing conditions, it makes sense to turn this thing on, yeah, and it will allow a certain amount of fluid onto the leading edge, prevent ice from building up. If you fly into icing conditions you weren't aware, you see ice forming on the wing, then you can turn it on, and the fluid will come underneath the ice. It will break the bond between the ice and the wing, and the ice will fly away.
Okay.
What we got now? Control for the thing. Yeah. Obviously, the reservoir. We need to know how much liquid we've got in the reservoir. So there's a contents indication there for your fluid. On/off switch. Yeah. So we can see whereabouts we're pumping it. What's we saying? Indicator lamp, yeah. High pressure warning. Maybe that we've got a blocked filter. Yeah, that'll just give us a warning there. Again, the reset. We needn't worry about any of this. We need to know what the contents of the system are. We need to know that the system's operating, so we'll have an indicator light to tell us whether it's on or off. Yeah, and we'll have a warning lamp to tell us that the system's operating or not operating, as the case may be. Don't worry about the light. We'll look at that after lunch. Yeah, so that's just our control panel. Basically, all we've got is a contents indicator and a pump. Yeah, we switch the pump on, and that's going to push fluid from the reservoir out to the proportioning unit that's going to send it to each of the panels. There is something in the notes, and I'll double check in a minute. I think the pump has to be run for 30 seconds every, is it 90 minutes, I think. And all that's doing is making sure that the system is fully primed, so when we need it to operate, it will.
Yes, you are right. 30 seconds.
I was right, was I?
90 minutes, yeah.
Hey!
Page number 45.
First time in a long time. Yeah, don't worry about that. Don't worry about that. The distributor panel, yeah, we'll have a look at that in just a second. Plastic pipe work. Don't worry about the sizes of the pipe. Filters in the system, we mentioned that. Yeah, 30 seconds every 90 minutes. 30 seconds every 90 minutes, and away we go. So Mr. Pilot, flying along, knows how much he's got, goes into icing conditions, switches the system on, and it will send the right amount of fluid to where it needs to be. Right, very important, this bit. Yeah, the distributor panel is the leading edge of the wing. Yeah. So if we've changed a distributor panel, we need to make sure that it's been fitted properly. It's got a nice smooth profile. Yeah, and to double check that, to ensure that everything is okay, if we change a distributor panel, we must carry out a flight test on the aircraft. Yeah, to make sure that the aerodynamic abilities of the aircraft hasn't been affected. Yeah, so definitely stick a highlighter through that. The fact that if you change a distributor, checks got to be made to ensure that you've got smooth, continuous profile. And on top of that, we must carry out a flight test to check out the stall characteristics of the aeroplane. Yeah, in other words, the handling of the aeroplane. Has anybody got any questions there on any of that little lot? Only other thing there, looking after the panels, just make sure that they're not dented, not damaged. checking the system, just making sure that the perforations are allowing the fluid to weep out when it's running. And if we're not going to use the system, it says to make sure it's drained. But again, that depends whereabouts you're operating. So I wouldn't worry about that too much. And that was it for our ice protection, the different systems. Yeah. What we'll do this afternoon, we'll have a look at the ice detection side of things. And the windscreen and probes and engine protection. Yeah, so we're smack bang on course. Has anybody got any questions at all? Otherwise, we'll stop for lunch there. Okay then. Right, I make that 12:05 my time. Do you want an extra 10 minutes today as a treat?
As per your convenience.
Yes.
Yeah, well, I'll make that on my watch. It says 17:51 Kathmandu time. So 1800.
Yes.
So if we stay back at 1900 your time.
All right.
Okay. So
Okay, sir.
that's
Go ahead, sir. No problem, sir.
that'll be 12:50.
Okay.
19.
Yeah. So that'll be just about what we want. Is everybody okay with that?
Okay.
Yes, sir. Yes, sir.
Yeah.
Okay, no
1900
problem.
your time, which is 13:15 my time.
Okay.
Okay, sir. Okay.
See you.
Lovely. Right. Enjoy your lunch. I'll see you in a few minutes.
Okay.
Have a nice lunch, sir.
Okay. All right. Hello, hello, hello. Have we got everybody back?
Yeah.
Yes, sir.
We're back.
Everybody can hear me. Can everybody see the presentation still?
Yes,
Yeah.
sir.
Fantastic. And
Yes, Jim, we can.
has anybody got any questions on anything that we covered up to lunchtime?
Yeah, Jim.
Yeah.
The fluid ice protection system uses nylon pipelines. Yeah.
The fluid one, yes. Yeah.
Any special reason for that?
Wait. Just they're a lot more flexible and they're a lot lighter. And that's the only thing.
Yeah. Okay. Thanks.
Right. Lovely. If everybody's happy, we'll plod on. We've looked at the formation of ice, how we get the ice, and we've looked at how we're going to get rid of that ice if it does form on the aeroplane. But one of the things that we need to know is whether the ice is actually forming on the aircraft or not. We could be flying in nice, beautiful, sunny conditions above the hills, in complete ignorance of ice forming on the aeroplane until it becomes too late. So what we need to do is to provide some sort of means of detecting ice that is starting to form on the airframe, so we can do something about it before it causes any problems for us. So as well as the protection systems, we've got various ice detection methods that we're going to use on the aeroplane. Again, like we said before, because it's a protection system, we need it to be simple, we need it to be effective, and I've just seen a young girl jogging past my window, and that was quite nice. But that's by the by. We need it to be a nice, simple, but effective and efficient form of detection. So depending on the size of the aircraft, type of the aircraft, it depends on the type of detector that we're going to find fitted to the aeroplane. Yeah. We'll have a look at each of the individual ones. Yeah, but the sort of detectors we get, a simple spotlight down to a vibrating rod. Yeah, and each of them, as we'll see, are very good at doing the job that we require them to do. So going from the simplest system, is just a spotlight. Yeah, spotlight fitted to the fuselage of the aircraft, lined up with the leading edge of the wing. And what we do is, simple enough, we look out the window, turn the spotlight on, look out the window, and visually examine the leading edge to see if there's ice forming on the aircraft. It's a good system. The only way it'll fall down, it relies on somebody having good eyesight. Yeah, so long as we shine the light down the wing, look out the window, so long as you can see where we're looking, we can make sure that there's no ice there, or if there is ice, we can do something about it. Obviously, in an aircraft this size, it's going to be a bit awkward for the flight crew to look down, so somebody's going to have to walk into the cabin and walk down and just look out the window. Yeah. Keep the B2s very happy. They get involved. It's a simple lamp. Yeah, simple spotlight. Yeah, just there's not a lot else I can say about it. It's just a spotlight that's set at the correct angle that's going to shine down the leading edge of the wing. Yeah. Even on your larger aeroplane, you can still have the same thing. Yeah. Turn the spotlight on. Get one of the cabin crew, have a look out the window. Is there any ice forming? No, there isn't. As easy as that. Sorry, I keep getting pinged. Yeah, easy as that. Nothing to it. Another type of detector that we might come across is what they call a serrated rotor. Again, it looks complicated, but it isn't. It's a very simple little device. Yeah, it consists of a knife edge, yeah, a fixed knife edge, and just forward of that knife edge is the rotating rotor. The serrations, just the little grooves down the thing. And what happens is, as this thing is sitting in the airflow, if it's rotating, yeah, and it rotates at a certain speed, and everything is quite happy. If we enter icing conditions, ice starts to build up on the rotor, and obviously, as the rotor's turning, as it meets the knife edge, any ice that's forming is going to get shaved off by the knife edge. The thicker the ice gets, the heavier the icing, the more resistance there is going to be to the rotation of the rotor. Yeah, so the knife edge is trying to shave off the ice. Ice is getting thicker and thicker. This thing now is going to slow down. Yeah, on the back side of the rotor is a little motor that's turning it, and as that motor as the ice creates the resistance to the rotation, yeah, what happens is the torque reaction makes a set of contacts, and that puts on a warning caption in the cabin, and that warning caption tells the pilot you are in icing territory, you've got ice build up, you need to do something about it. So all that's happening, these little contacts making a circuit, light goes on, pilot turns on his ice protection, whatever method that is, gets rid of the ice on the wing, and away we go. As we start to exit the icing conditions, yeah, obviously the ice on the rotor is being shaved away. Yeah, the less ice that's on there, now this motor can start to, or the rotor can start to speed up, and eventually it'll match the overcome the torque reaction, I should say, my apologies. It'll overcome the torque reaction, the contacts will separate, and the ice warning light will extinguish. It's as easy as that. They are a common little thing. Yeah, you do find them, but they are, again, very efficient. Good system. Very simple. So just the motor mounted to the fuselage. Yeah, the rotor protrudes. Rotor's turning. As the rotor's turning, it's the knife edge. Any ice build up, there's a resistance caused, and as that resistance gets stiffer and stiffer and stiffer, it's going to cause the contacts to either make or break, whichever way it's set up. Yeah, and as the contacts make or break, it's going to put on the warning light in the cabin. Hello, Mr. Pilot, you're getting icy. Do something about it. And again, just showing the setup of the motor in the aircraft in the fuselage. Yeah. Terminal blocks. That's to keep the B2s happy, so they see something electrical. Makes them feel wanted. And away we go. Yeah, nice, dead easy, dead simple. Yeah, the vibrating rod detector is again a very common method of ice detection, and with the vibrating rod detector, what we get is a little pin, yeah, sticking out the detector, and that pin vibrates at a particular frequency. And while it's vibrating at its normal frequency, it's quite happy. if we fly into icing conditions and ice starts to build up, obviously that vibration is going to come across resistance now. And as that resistance to the vibration gets bigger, again, it's just going to set off a signal in the flight deck. It's going to illuminate a warning light. And again, the crew have been notified that they're going into icing conditions. Easy as that. Easy as that.
Seems easy, but question very difficult.
Say again?
Figure and everything seems easy, but question becomes very difficult. Exam question becomes very difficult.
No.
Won't be?
No. It's, you know, what sort of question could they ask you? What type of ice detector might you find on an aircraft? A plastic bag full of water, a vibrating rod detector, or I don't know, packet of cheese and onion crisps. You know, it won't be anything too complex. It'll be something fairly simple.
Really, Jim?
Yeah.
Will be asked such kinds of question? I don't think. It's level one or level 2? You are asking just level 1 question.
I sent out this morning, and bless him, Yadav should have forwarded it on. I sent out a copy of the questions again, but the level for the different subjects is on there now.
Okay.
Yeah, so in red on that sheet, that is the levels of the questions.
From this section is level 3.
Level 3?
Yeah.
So, Jim.
So, but again, you know, when you're looking, just think, well, what sort of question could they ask? You know, it's not going to be anything too dramatic. It can't be. Right. Sorry, I'm distracting myself here. I'm doing 3 things at once. Lots of people trying to get into our lesson. Yeah, in the vibrating rod detector, yeah, there's a little heater in there as well. So the vibrating rod will carry on. It'll meet it. It'll put a warning light on in the cabin, and at the same time, a little heater is going to come on and melt the ice. So long as we're still in icing conditions, the ice is going to reform, and it's going to alter the frequency of vibration again. Heater will again melt the ice, you know, and this cycle will continue for as long as we're in icing conditions. Once we're out of icing conditions, heater melts the ice off. If there's no more ice there, then the head will return to its original frequency. And the last thing it's on there is that normally, as with anything in aviation, we're always going to have some sort of backup. So wherever you've got these ice detectors, generally you're going to have more than one. So there's normally going to be a couple of these dotted about the place. Yeah. Whereabouts they're located kind of depends on the aircraft type. Ours, we used to have one on the fuselage and one at the base of the fin. Other aircraft, you'd get them on the forward fuselage like this, and that's all it is. Little thing vibrating at I think it says about 40 kilohertz, whatever that means, some sort of B2 language, and vibrating away. Ice builds up, slows it down. That puts your warning light on to say that you've got icing building up. heater comes on, melts the ice. So long as you're still in icing conditions, the warning's going to come back on. Again, if we get a failure in the system 1, it'll let us know. If we get failure in system 2, it'll let us know. Easy as that. The hot rod heater, sometimes known as the black rod type heater, or the hot rod. Yeah. So that's why you've got a picture of a hot rod, and that chap there is known as the black rod. Just a UK thing, so don't worry about the pictures. Yeah, all the rod is a little rod that sticks out into the airflow. Yeah. If ice forms on the rod, yeah, the pilot looks out and he sees the ice on there, turns the heater on, yeah, melts the ice, turns the heater off, and watches for the ice reforming. Depends how long it takes for it to reform. Depends on the level of icing that we've got. And then, as it says, because he's that busy looking out of the window at the rod, watching for ice forming, he doesn't see the big mountain in front of him. But this is your hot rod. That's the thing there, sticking out the side of the fuselage under a convenient transparency for the pilot. And it is just, as the name suggests, it's just a rod that sits out the detector mast, to call it here, just a rod. Inside there's a heating element. Yeah, so as the aircraft's flying along, if we hit icing conditions, ice starts to build up on the rod. Pilot's having a look out the window every now and then, sees the ice forming, turns the heater on, yeah, little internal heater. That melts the ice. Heater goes off, yeah, and he watches to see how long it takes for the ice to reform on the rod. Again, as easy as that. Yeah. Obviously, for nighttime, we need to make sure that you can see the thing rather than shining a torch out or whatever. So at nighttime, for night operations, there's a little lamp at the base of the rod. We can turn that little lamp on, and that will illuminate the rod. And again, you should be able to see any formation of ice.
Hello, Mr. Jim.
Yeah.
In this hot rod ice detector system, the pilot will observe this hot rod, or he will be informed that the airplane is covering from ice. This is only the indication, no?
That's the only indication, yeah. Just looking out of the window and seeing if there's ice on that rod.
In this case, if there is ice in the rod, then he will activate the whole system of anti-icing, or this hot rod only?
No, if he sees ice on that rod, yes, he'll turn the system on. He'll turn the de-icing system on.
Whole system on?
Yeah.
Okay, thank you.
What I would say with this type of system is it's quite old. You'll find it on older aeroplanes. Most of the aircraft that I've come across use the vibrating head method, because that is simple, it's effective, it's efficient. Yeah, there's not a lot can go wrong with it. So that's the one that I've come across most on aircraft I've been involved with. The other systems, the serrated rod detector, the hot rod, they are found on older aircraft. You might come across them, you might not come across them, but at least if you know what they're doing, how they operate, you're on a winner.
Jim.
Yeah.
Do you have to remember this vibrating frequency, that resonant frequency?
Not that I know of, no. No, you just need to know that it's vibrating at a frequency, and it's the buildup of ice that alters that frequency.
Okay.
That puts the warning light on. Yeah. With the hot rod system, you haven't got a warning light. It is purely down to the pilot observing what's going on out of the window.
No, he's talking about this vibrating rod
Yeah.
system.
Yeah. There's mentioned so 45 kilohertz resonant
45?
frequency.
Yeah, no,
40.
no. Don't worry about the.
Okay.
You just know that it's vibrating at a particular frequency. You don't need to know what the, because that frequency could change between aircraft. Yeah, that type of probe might vibrate at around about 45 kilohertz. This one might at 40 kilohertz. Yeah, so because you've got that slight difference, we're just going to say at a frequency. We won't stipulate what frequency.
Okay, so in the indication only shows in the vibrating, not in the rod, hot rod. Only
Not in
one
the
indication.
this one.
Yeah.
The serrated rotor, that will give you an indication in the cabin.
Okay.
Yeah. So as the ice builds up and that rotation slows down, yeah, the switches will make or break whichever way it's set up, and that will put on a warning light in the cabin. The pilot will then switch on the ice protection system.
Got it.
The vibrating rod, exactly the same. As that frequency changes due to the ice build-up, yeah, the pilot knows he's going to get a warning light, so he knows that he's in icing conditions, so he can turn the icing system on. With this one, all he's doing is looking out of the window to see if there's ice forming on the rod. Yeah, it won't give him a warning light in the cabin. He's just got to use his eyes.
Excuse me, Mr. Jim.
Yep.
Please, can you tell me the time period of how the time will be triggered in the vibrator rod ice detector system?
Say that again, but slowly.
Sorry, can you explain again the time period of the time will be triggered at the vibrating rod ice detector system, sir? How it will be triggered, sir? Time period triggering.
The vibrating rod.
Yes.
Yeah, this thing, this little probe here, is that, and that is driven to vibrate at a particular frequency. I think it says 40 kilohertz in the notes. Yeah, so this thing is vibrating at 40 kilohertz. If we get ice building up on it, let's we have some. We'll have some ice. So we'll get ice building up on the probe. Yeah, that ice is going to change the frequency at which it's vibrating. Because we've changed the frequency, that via the electrical connector thing is going to put on a warning lamp in the cabin.
Okay.
Yeah, the pilot will then turn on his anti-icing system. At the same time, yeah, as he turns on the icing system, there's a little heater inside the probe here, and that heater will melt the ice that's built up. So once it gets to, let's say it's vibrating at 40 kilohertz, yeah.
Yes, I see in our aircraft. Yes, it's installed in our aircraft. In the Airbus 320, I have seen. Yeah, but I want to know that the actually time period, how it will work the time period, sir. Just here is written in the book that the ice warning signal is received during the time period. The time will be triggered. How will be triggered, sir? That's only I want to know. Actually.
When the warning light comes on, when it makes the warning light, yeah, it'll turn the timer on for the heaters, yeah. So the heater will run, it'll melt the ice off, and the timer is there just to if we're still in icing conditions, it'll just give the time for the ice to reform, and it'll keep the warning caption on, so he knows he's still in icing.
Okay, sir. Got it, sir. Thank you, sir.
You sure?
Yeah, sure, sir. Sure.
Okay. Anybody else got any? Yep. Okay, so the hot rod, we've talked about that. Right, for our ice detectors, if we've got heaters in there, or for any of our probes, as we'll come on to, yeah, we need to make sure that any covers or blanks are removed before we check the heaters. So when you're doing your ice detector checks, yeah, the heaters are gonna run. If you've still got your covers, your probes on, there's a possibility that the cover will melt and damage. The other thing, yeah, obviously good practice. The covers need to be in a contrasting colour to the aeroplane, yeah, and preferably with flags or streamers on them, so that they're not left fitted to the aircraft when it goes flying. Yeah, always good practice that.
Yeah, excuse me, Jim.
Yeah.
Yeah, what does this detector uses? DC or AC?
Digital's normally DC.
In case of both hot rod either vibrating rod ice detector, DC. Hello.
The hot rod detector. I would guess DC because it's going to come off a battery supply.
Yeah.
I wouldn't worry about it, but I'm not an electrician to trade, but I would say DC.
DC.
Yeah, that's what I'd say.
Yeah. Okay. Thank you.
Yeah. So any detectors, any probes and all that, yeah, we need to make sure that the covers and blanks are off before any heaters are operated or checked. Lovely. Right. Maintenance of these things. Again, we follow the maintenance manual. Certainly, your vibrating rod. There'll be a functional check for that. The procedure will be laid down in the manual. Basically, you'll turn the thing on. It'll be vibrating. You'll put a little bit of resistance against it, and just make sure that the pardon me, the warning light comes on. Not a lot else you can do there. The serrated rotor detector, again, this is the B2 guys will come out and check this using a special salt torque screwdriver. Yeah, they'll turn the rotor. Yeah, they'll be spinning the rotor, and then, as it says on the screen, just slightly push on the screwdriver, give a bit more resistance. That's going to slow the rotor down, and you're just going to make sure that the warning light comes on in the cabin. Yeah, checking the heaters. Again, just going to flick the switch, flick the system on, and just with the back of your hand, just make sure that the heaters are coming on and are operating. And again, making sure that we remove any covers and blanks before we do the heater check. I'm sure you're all aware that if you're going to check anything for temperature, always do it with the back of your hand. If you try to use your palm, if the thing's hot, your hand instinctively closes. Yeah, so all you're doing is grabbing onto something that's really hot. So checking for the heaters, always use the back of your hand. If the elements are on, if it is hot, all you're going to do is singe the hairs on your knuckles. Asked my daughter that one. She went to university last year, and she was staying in a flat. and in the flat there was a cooker, and she turned the cooker on, and she put a hand above the hot plate to see if it was warming up. And I told her, never ever do that. Always use the back of your hand to check. And one of her friends was standing next to her, listening to me shouting at my daughter. And the very next day, she did exactly what I told her not to do, and she burnt her hand quite badly on the palm. Yeah, just touching the hot plate. So always, you're probably well aware of this. You probably know it, but if you're checking anything for heat, always use the back of the hand. There you go. Top tip. One of Jim's top tips for today. Anybody got any questions on your ice detection then? No. Dead easy, dead simple.
Yeah, excuse me, Jim.
Yeah.
Yeah, I've got a question.
Uh-huh.
Yeah, the flow rate of anti-icing fluid is determined by flow control valve or flow control tubes.
The flow control.
Yeah, it says the flow rate of anti-icing fluid is determined by what? Is it by flow control valve or flow control tubes?
Flow control valve, maybe.
Well, that's not one of our questions out of our books, is it? But I think what they're getting at is the proportioning unit, and the proportioning unit is saying how much fluid is going to each distributor. So I'm guessing that's what they're talking about. So I'm guessing that's what they mean by tubes. But quite frankly, that is a shit question.
Yeah, I just found out the question and just asked normally, casually.
Yeah, with all these question banks that are kicking around, be very careful, because a lot of them they're badly worded questions, and they can mislead you. Yeah, they're good revision tools, but just be careful. And certainly the ones that come with the answers, be very careful with those, because a lot of times, in my experience, the answers are wrong.
Yeah, okay.
Yeah, I'm not saying don't use them. Obviously, whatever helps you, but just be aware that sometimes they're not as good as they could be.
Yeah.
But I am just the wording of that question is awful. But I'm guessing they're talking about the proportioner, which is governing the amount of fluid that's going to each distributor panel.
Yeah, it is then a proportional unit. Proportional unit.
Yeah.
Yeah. Okay. Thanks, Tim. Thanks.
Yeah, because up to the proportioner unit, you're going to have a rate of flow. That proportioner unit is taking the fluid and then sending it out to the different panels, so that the flow is going to be different there. Yeah, so you're looking at two halves of a system. Anybody else got anything?
It's written calibrated capillary tubes.
Yeah.
In the proportioning unit, it's mentioned calibrated capillary tubes. So the answer may be the flow control tubes.
Yeah, well, that's what I'm talking about, the proportioning unit. Yeah, there's a little metering head in there. Remember, we talked about that before break? But you're right. Yeah, those metering tubes are what gives each panel, that amount of fluid, and they're all held together there in the proportioning unit.
So answer is capillary tube. That is the capillary tube inside the distribution unit, proportion unit. Sorry.
Right. That is your proportioning unit. Yeah. That's what it looks like in real life. And what's happening is you're getting fluid from the main system coming into the proportioning unit. That fluid from the main system is coming into what they call a metering plug. And that metering plug is just a series of little, as somebody's just said, calibrated tubes. Yeah. So the main amount of fluid, yeah, these tubes are different sizes, so they're going to accept a different amount of fluid. And those tubes are connected to a particular outlet. Yeah, so let's say this tube here, this grey one, is connected to this outlet here. As the main amount of fluid comes in, that metered tube is going to take the right amount of fluid that it's been given, and it's going to direct it up through this outlet. In that outlet, there's a non-return valve. So, pardon me, the fluid that's going through that little tube up out there to the distributor panel is metered. Yeah, so it's getting the right amount of fluid that it needs. And obviously, depending on the calibration and the diameter of that metered tube, yeah, depends on how much flow you're going to get to your distributor panel. And that is your distributor panel. So again, it's just a bit red for highlighting. Yeah, proportioning unit, main feed from the pump. Yeah, that'll send fluid to the proportioning unit. The proportioning unit will then send the right amount of fluid, yeah, via that regulated bloody metering tube. Yeah, it will send the right amount of fluid to each leading edge panel. So this one might need, I don't know, 1 litre a minute. No, that's a bit much, but whatever amount of fluid it needs, yeah, the proportioning unit will make sure that it gets the right amount. This one might require, it's a smaller panel, yeah, it might require a lesser amount, so the proportioning unit will make sure it gets the right amount.
Excuse me, sir, it's the proportioning units mentioned in the book also.
The proportioning unit is, yeah.
Yeah, it's mentioned in the book also, sir. In page number 49, distributor, it's written under the chapter of distributor.
Right.
In first paragraph.
This, if you look at the screen, this is the proportioning unit that I've just shown you. Yeah. And this is what takes in the fluid and it sends it out to the different distributor panels. This is a distributor panel. This is the leading edge of the wing with lots and lots and lots of tiny little holes drilled in it, normally drilled by lasers. So when I turn my fluid system on, the pump will start running. It will push fluid down to this proportioning unit, and the proportioning unit will send the right amount of fluid to each distributor panel that's fitted to the aircraft. You with me?
Yes.
Yeah, you okay with that?
Yeah, okay.
Yeah. So when we talk about the distributor, we're talking about the leading edge panel. When we talk about the proportioning unit, we're talking about the item. Do you guys have jelly bean sweeties out there? And you put a coin in and you turn a little handle and the thing will deliver a handful of jelly beans to you. Do you have those?
We don't have those here, Jim.
No. I'm just trying to think of the best way to describe a proportioning unit. Yeah. It's just there to divide up the the amount of fluid we get. That's the fluid coming in, yeah, and your proportioning unit is just little pipe connections, yeah. So if I have a thin bore pipe here, yeah, a small metered tube, I'm only going to get a small amount of fluid. If I've got a larger diameter pipe, I'm going to get a larger amount of fluid, and that's what the thing's doing. It is just there. This is there to send the right amount of fluid to each individual panel that's fitted to the wing. It's a bit awkward because I haven't got anybody there to use as an example. But let's. Who's in front of me? I've got Sanjay Kumar in front of me. Now let's say Sanjay. I don't know. I can't see him. But let's say Sanjay's a big lad. Yeah, and he wants a beer. So he's going to get a big bottle of beer, and that's going to satisfy him. So because he's bigger, he's taking in more fluid. Navin, who's up there, he might be a really small guy, so he needs less beer. So he's only going to get a small bottle of beer. Yeah. The barman is the proportioning unit. He's going to hand the beer out. So he's going to say, Sanjay, big bottle, Navin, little bottle. So he's making sure that you get the right amount of beer. Yeah, and that's what your proportioning unit's doing. It's making sure that each panel is getting the right amount of fluid.
Okay.
Wonderful example, team. Yes, Jim.
Can't go wrong with beer.
We won't get beer.
I'll tell you, next time I come out, I'll bring some with me. I'll bring you a bottle in. We'll all sit and drink that, and we'll have a cookery rum.
So,
cookery rum with honey.
With honey?
Yeah, this is good for good in winter season.
I shall try that then.
You should try it.
Yeah. Yeah, just while it's there, this is the distributor panel, and it makes up the leading edge of the wing, and there could be 4 or 5 of these panels making up the leading edge. Yeah, and that's why when we change a panel, we've got to make sure that we flight test the aircraft to make sure that it's in alignment with the others, and we've got a nice continuous leading edge. There's no lumps and bumps sticking out. So we've been through the detection system. Happy with that and the maintenance thereof. Now, again, before I carry on, has anybody got any questions at all? We've all gone quiet, so that's good. Right. So the windscreens then. And the windshields. Obviously, it's quite important for the crew to be able to see where they're going. Yeah, as we're flying along, we want to make sure that, as I say, we can see where we're off to. So to prevent ice formation and again misting, people tend to forget that the windscreens will mist up and fog up. We're going to provide heating for the windshields. Yeah, if we didn't have that, it could be quite iffy. Yeah, don't take long for your ice to build up either. So we're going to put windscreen protection in there, and that windscreen protection is windscreen heating. Yeah, the windscreens are continuously heated. Yeah, so once we've turned the windscreen heater on. Having said that, on a lot of aircraft, it's actually automatic. As soon as you turn power on, the screens will start to heat up, and that heating is running continuously. Yeah. By heating the screens, yeah, we improve the impact resistance. This is well worth sticking a highlighter through as well, guys. Yeah, because we're heating the windscreen, and the windscreens are made of a composite plastics. Yeah, heating it, it doesn't soften the plastic, but it makes it more pliable, so it improves the impact resistance of the windscreen. So you're flying along, the screen's nice and warm. It's got that little bit of flexibility, so if it gets hit by a bird, yeah, it's less likely to shatter, unless it's a big bird. Yeah, so continuously heating the screens, yeah, that improves the impact resistance. For demisting the screen, we're just going to use air, and there's a couple of different methods of doing that. We'll have a look at in a minute. Yeah, so air blown over the screen for your demisting, and then we need to provide rain protection as well. And there are various methods of rain protection. We can use windscreen wipers. They're the most obvious, exactly the same as you get in your car. Yeah, back and forth. However, they become ineffective over a certain speed. So what we can do is use rain repellent. Yeah, again, just spray that onto the windscreen. Again, we'll have a look at rain repellent in a bit. And then a thing called a hydrophobic coating. That is applied at manufacturer, and again, it gives us an element of rain protection. So, moving on from that, yeah, our transparencies, yeah. Side windows aren't so critical as forward windscreens. We need forward vision in the aircraft. We need to see what's coming at us. The side screens aren't so critical. So your forward vision, we're going to provide that that heating, that element of heating in there. This is just showing us how the windscreens are actually constructed, how they're actually made up. The outer screen, yeah, is made up of glass. And then behind that glass, we have a conductive coating. And that conductive coating is what we're going to use for heating the windscreen. Yeah, we're going to run electricity through that conductive layer. Behind that, we've got vinyl, plastic, and then the next layer again is glass. Yeah, same with the adjacent screen. Yeah, those two are going to be the same. This one, the side screen, yeah, you can see it's a different material, but there's no conductive layer in that one. Again, we've got forward vision. Yeah, so we're going to have a conductive coating, and again, the outside layer, glass. Yeah, this one, the heat is a bit more embedded in the base of the composite, if you like. Yeah, whereas the heaters on the windscreen are adjacent to the outside layer. What else we've got to say then? Yeah, windscreen put in, and it's wired into the aircraft mains. Aircraft mains, the main power supply. Yeah. Within the screen, yeah, we've got our little heater terminals, yeah, where we're going to connect into, and also attached to the windscreen are overheat sensors, yeah, and controllers. So the pilot has got his windshield heat. Yeah, the thing will turn on. In this case, he's got the option for his side windows, but his windshield heating, that normally comes on as soon as you turn power on. yeah, and the windscreen will start to heat up. It takes round about 4 minutes to introduce that heat into the windscreen, and the reason for that length of time is to prevent thermal shock. If you had a really cold windscreen and you applied heat directly straight to it, yeah, the screen would just shatter, and that is your thermal shock. It's about like having a very cold beer glass and you dip it in a sink full of really hot water. The glass will just shatter. It has thermal shock. So by gradually warming the windscreen through, we prevent that thermal shock damage. And the windscreen will go up to its operating temperature. From there, it's continuously heated. Heating going through, and there are a couple of, I can't remember, I think it controls around about 40 degrees C. The controls, just excuse me 1 second, I don't want to give anybody the wrong figure. Yeah, control unit, yeah, controls at around about 40 degrees C. Yeah, if we get a failure in that controller, the temperature starts to rise. There's a secondary controller in there, and that's going to control the windscreen heating at around about 55 degrees. Yeah, so you're still going to get your windscreen heating, but it's just going to be controlled by a separate controller and controlled at a slightly higher temperature. So 40 is your baseline. That's what the windscreen's normally heated to. If you get a failure in controller 1, controller 2 will take over, but it will control at that higher temperature of around about 55 degrees. To let the crew know that they've got a problem, they'll get an indication in the cabin saying that they've got a windscreen overheat. Yeah, so that's your screen. Yeah, this case they turn it on. Windscreen heating on. Quite happy. If you get the overheat, the controller, the second controller will take over. That will look after the windscreen, but it'll control at a slightly higher temperature. But you will get a warning caption just to say that you've overheated somewhat. So worth knowing that there's 2 controllers. Failure in one, the other one will take over, but it will control at a higher temperature. Okay with that? Lovely. Right. The windscreen themselves then. Yeah. As windows get older, we've got the heating element built into the windscreen. Over a period of time, the resistance to that heating element generally increases. Yeah. So what we need to do is to adjust the voltage for the windscreen heater every so often. So again, our little B2s will make themselves useful. They'll put the coffee down, they'll put the cards down, they'll come out of the cupboard, and they will go away and they'll adjust the voltages on the windscreen. So the transformers used with new heat systems are given a range of voltages. So they'll check the resistance, they'll adjust the voltage to the correct level, and away we go. We're quite happy. Over a period of time, over the years, yeah, the windscreens age, the resistance in that heating element changes. So every so often we need to recheck the voltages, alter the voltages to make sure that we've got the correct voltage supply for heating the screen. Yeah. So again, in the maintenance manual, there'll be I might have a picture of it actually. Just yeah, come back to that in just a second. Yeah, there's a chart that tells the the B2s what the voltage requirement is for the heaters for a particular resistance, and they'll go out and they'll tweak that and they'll adjust it. Yeah, just showing that we've got a fault in the window heater there. This is the thing I was on about. Yeah, you'll get a new windscreen. Yeah, tells you the bus-to-bus resistance, the minimum and the maximum. So they'll go out and they'll adjust that. What the voltage required is. Yeah, it tells you what temperature the windscreen is going to be heated up to. Yeah, and whatever terminal strip tap is. Secret electrical code, terminal strip taps. Yeah, but we can adjust it. We adjust the voltages to make sure that they marry up with the correct resistance parameters laid down in the manual. Boom. The other thing that's worth mentioning is if we get a failure in the controllers, failure in the elements, we can get arcing. Yeah, windscreens, if you get moisture on there, you can get arcing, and that arcing will lead to crazing of the windscreen. You can get a burnout. You can see the connector here has had a bad burnout, and that burnout has started the cracking of the windscreen. Yeah. Again, depending on the limits given in the AMM, we might be able to live with a little bit of damage to the windscreen. Certainly chips, gouges coming out of it. We'll look in the manual. We'll look up for the limits, and that'll tell us whether we've got to change the screen or not. If we need to, so be it. Replace the windscreen. We'll cover that in structures, but we'll replace the windscreen, and again the B2s will have to come, connect it into the mains. They'll do all the resistance checks, all the what's the word I'm looking for? The voltage adjustments, yeah, until everything's sweet. Don't think there's much else to say on windscreens. Transformers, changing it, adjusting the voltage tappings. A little bit on maintenance, just in the notes. I'll just go over that just to make sure that we've covered it. Within the windscreen, because it's made up of layers, sometimes those layers can start to separate or delaminate, and we end up with bubbles appearing in the windscreen. Again, depending on where they are and the size of them, they could be considered acceptable. So have a look in the AMM, see if they're within limits and if we can live with them. Arcing, we've just mentioned that. So normally occurs near the bus bars. Heat from the arcing causes brown and black marks in the interlayer or cracking of the windscreen. Again, if you do get that damage, we're into replacement more than likely. Your windscreens, because they've got this conductive layer in them, they tend to look like a greeny, bluey green sort of colour. If you catch them in the right light, you can see the colour. That is a deliberate part of the makeup. So just make sure that the colour's nice and uniform and even. If there's any discoloration of the windscreen, again, that could be indicative of a fault. Yeah. Yeah. Again, not a lot else to say on the maintenance side of it. Yeah. If we change a windscreen, obviously we need to carry out the heater test, make sure that it's working okay. Carry out your functional checks whenever the manual calls for it. it gives you an example of the test overheat and the power test that we need to carry out. But again, don't worry about that. The testing of the system is going to be strictly in accordance with the AMM. Just be aware that we do need to carry out those checks when we change the windscreen. Anybody got any questions on screens then? No? Right, what we'll do there, guys, just before we move on to the next subject, we'll just have a 10-minute break. Yeah, because I don't know about you, my eyes are starting to feel the strain of looking at the screen. So we'll just have 10 minutes. Yeah, 14:15 my time, so 14:25 my time. 10 minutes, and then we'll come back and we'll get through the rest of this. If nobody's got any questions.
Okay, sir. 10-minute break, sir. No problem.
Okay, 10 minutes then. Okay, I've got everybody back.
Yeah.
Excellent. And what these two, and we'll plod on. We're aiming towards the end of the. What I'll do, I'll just work through rather than have a tea break. Is that okay? Milan, you've got your hand up. Everybody's got their hand up. Okay, so if you're happy enough with that, I'll just carry on to the end, and then we'll probably finish a few minutes earlier than normal. That'll give us a chance at the end. So if anybody's got any questions, they're more than welcome to ask.
Okay.
Okie dokie. Right.
This you taught us, and it is very easy to understand. We understand, but can we pass the exams of level 3 with this understanding? Because you don't highlight anything and all, though we understand everything you teach. So can we pass for that?
Yes.
We need
as long as you read through your notes. Yeah, I can't say, oh, you've got to highlight this, you've got to highlight that, because we'd just be highlighting the whole book. But all the points I've given you, and with the questions that I'm sending out as well, to help you with your revision, yes, I've got no doubt at all that you will pass.
Thank you.
Jim, the questions will come from this book, these books only, I think. Am I right?
Yes. Yeah, they'll only come from the AST books. They will not come from anywhere else.
Okay, Jim.
Yeah. Yeah, and so, you know, that's what we're saying about don't get too swamped down with questions from other places and start thinking outside. Just stick with the material that you've got, because that's where the questions will come from. Okay then, let's plod on then if we're right. Yeah, we've looked at all the ice protection side of things. Now we need to have a look at rain protection. What's rain going to do for us? Apart from the impact damage, it's just going to obscure our view, yeah, so we can't see anything. So what we need to do is to put some sort of system in place where we can get rid of that rain, where it's not going to impede our vision too much. And that's what the next little bit is about, is the rain protection side of it. Again, rain protection, very, very simple. Yeah, it doesn't need to be difficult, and it isn't. The most obvious form is windscreen wipers. Yeah, back and forth, and just wiping the rain away from the windscreen. To help the windscreen wipers, we can use rain repellent, and that is just a chemical we spray onto the windscreen, and it will help with the clearing. The wipers get rid of the rain. Probably the best method that we've got is by blowing air up in front of the windscreen. So as the rain comes along, it doesn't actually hit the windscreen. It gets blown away by the bleed air before it gets there. Very, very, again, effective, efficient method of rain removal. I know that's a military aircraft, but it's there because you can actually see the vents in front of the windscreen, which it was the only picture I could find showing them. And then the other type of rain protection that we put on is what they call a hydrophobic coating. And that hydrophobic coating, it's put on at manufacturer, and again, it just helps dissipate the raindrops as they strike the windscreen. Yeah, so raindrops form on the windshield, pilot's vision's reduced, can be obscured. Get rid of that rain, wipe it off using your windscreen wipers, blow it off using bleed air, as we just said. Hydrophobic coating, Yeah, special coating put on at manufacturer and refreshed every so often at maintenance, and chemical rain repellent, which we spray up onto the windscreen. Yeah. Windscreen wipers, dead easy, no different to what you get in your car. Pardon me, sorry, I've got so much stuck in my throat. Yeah, the wipers, what can we say about the wipers? Yeah, the wipers, you've got your wiper blade, your rubber wiper blade that's in contact with the screen. That's attached to a wiper arm, and the wiper arm is driven backwards and forwards by a wiper motor. Yeah, the pilot and the co-pilot wipers are generally independent of each other. Yeah, so if you had a failure in the pilot side, at least the co-pilot could see out. If you had both of them operating off the same system, if you had a failure, then you've completely lost your vision, and that could spoil your day, really. So they're normally independent of each other. The blades are held against the windscreen by a tensioning arm. Yeah, and again, I might be getting ahead of myself here, but we check that tension using a spring balance. So when you come across that, again, make a note of that one. Yeah, so the wiper blade tension checked using a spring balance. Wipers themselves turned on and off. Yeah, 2 speeds, low speed and high speed. Again, you get the same sort of thing in your cars. Depending on the amount of rain that you've got coming down, you can have a slow, lazy sweep of the windscreen wipers, or if you select high speed, they'll be going back and forward like a thing possessed. Yeah, switch the wipers off, and they're sitting there ready, and then we have a park position for the wipers as well. Once they're in the park position, they just drop down that extra little bit, and they're clear of the windscreen itself. Yeah, so we've got park off, low and high. We'll come across rain repellent later. Yeah, so your motor, your wiper arm tensioned to hold the wiper blade assembly against the screen. Yeah, and as we turn on, the wipers all remove any rain. Like I say, unfortunately, the wipers become inefficient at higher speeds, so we need to give additional assistance to the wipers as well. And we'll have a look at that.
Excuse me, Jim. I have one question, please.
Yeah, please do.
Sir, what is the difference between the wipers off and park position?
The off position. Hang on, I'll just go back a bit. The off position. Can you see how the wiper's sitting slightly up on the windscreen there?
Okay, sir. Yes, sir.
Yeah, if you're in the park position, it'll drop down a little bit, so it's out of the field of vision.
Okay, sir. Okay, sir. Understand.
Yeah. It won't drop off the windscreen, but it just goes to a slightly lower position.
Okay, sir. Okay, sir.
So,
okay, sir, understood.
So currently is in park position in this picture.
That's in the yes, I'd say so.
It's in the park position, right?
It looks it, yeah.
Yeah.
Park or off, sir? I'm confused.
Out of visibility screen is off position, right?
Hang on a minute. Yeah, so if you go into the park position, yeah, that's going to drop down a little bit, so it's completely out of the line of vision. It's not interfering with his view. If you go into the off position, it'll raise a little bit, and then obviously on the wiper's going to be sweeping backwards and forwards. Turn it off, it'll go to the off position. Turn it to park, it'll just drop down that little bit more, so it's completely out of view. Yeah.
Yeah.
Okay. And in high speed, it will not work when the aircraft is in high speed.
Yeah. If you're in the off position, it'll be something like that. Yeah. If it's in the park position, it drops down a little bit. Yeah. So it's just out of his field of view. Low speed, yeah, you're just going to go backwards and forwards at a nice steady pace. High speed, woof, 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 woof. Yeah, it's going to be backwards and forwards very, very quickly. Yeah. Most of you guys drive bikes, don't you? But on a car, you get 2-speed windscreen wipers. Low speed, nice and steady and gentle. High speed, it moves a lot quicker. And we use the high speed in heavy rain, to get rid of it.
Actually, I'm asking when the aircraft is in high speed, the motion of the aircraft. So this wiper will not work. That I'm asking.
No. The what happens? The higher the speed of the aircraft, the blades tend to get lifted off the windscreen. Yeah. So it's not very efficient at all, which is why we always have additional methods of rain removal to help the windscreen wipers.
Okay.
Yeah.
But don't forget, when you're looking at a high-speed aircraft like that, they are generally flying at altitude, and once you've gone above whatever it is, 30,000 feet up into the stratosphere, the higher levels of the troposphere, you haven't got any rain there. Yeah, you've gone above the clouds.
What about the helicopters, rotorcraft?
What about them?
Windshield wipers.
Yeah, helicopters have got windscreen wipers.
So they don't have anything other than this wiper to protect from rain.
They might do with it. They might have some of the stuff that we're just about to come on to.
Okay.
Yeah, the windscreen wipers are good. They will clear rain up to the aircraft going to a certain speed, but then once you get beyond that speed, they lose effectiveness. If you think of a helicopter spends. Can whoever's got the mic on turn it off, please?
Mic on, sir, please off गर्नुस् न है.
Yeah, with a helicopter, that's going to spend most of its time flying at fairly low speed. They don't go that quickly, and it spends a lot of time working in the hover. So you haven't got the forward airspeed to blow the rain off the windscreen. So the helicopter's got windscreen wipers on it, yeah.
Okay.
Okay with that? And again, don't forget, your aircraft operating at high speed, a lot of the rain is going to get sort of diverted from the windscreen just by the forward speed of the aeroplane. But because the wipers aren't very effective, we're at higher speeds. What we do is use other methods of rain removal to back them up. Probably one of the favourite ones is the chemical rain repellent. We'll look at that in a minute. Bleed air, blowing the rain away using bleed air. That bleed air forms a protective layer of air in front of the windscreen. So as the rain comes in, it gets blown away before it can meet the windscreen. So it's not going to impede the pilot's vision. The hydrophobic coating that we were talking about is a special coating that's applied during manufacture. Yeah, and that special coating, what it does is, as the rainwater hits the windscreen, yeah, it tends to splatter and disperse, and it forms very small droplets and obscures your vision. The hydrophobic coating, yeah, keeps the raindrops in a large format, keeps the water together. So now you get large drops running down the windscreen, and you get a much better view. And obviously, having large raindrops, if you operate your windscreen wipers, that's going to get rid of that rain a lot easier. Your hydrophobic coating, like I said, it's applied during your manufacture, keeps the drops in large form. That rain runs away very, very easily. Every now and then we need to refresh that hydrophobic coating, and there are certain liquids that you can buy specially designed for doing that. Rain-X, there's one of them, and all we do is apply that to the windscreen, rub it in a nice even coating, and that just refreshes the coat that's been applied at manufacture. And as you can see there, fairly sunny day, but you get a nice view from the cockpit. And if it did start raining, the rain would stay in large drops, and you'd still be able to see, and you wouldn't crash, and nobody would die, and everybody would be happy. Okay with that? Hydrophobic coating.
Tim, this hydrophobic coating is applied over the screen during manufacture only. Is it sufficient through the whole operating time?
No, that's what I've just said. Every so often we need to refresh it. So what we do is we get a chemical that's designed by the manufacturer, and we just rub that into the windscreen, and it refreshes the hydrophobic coating. Yeah, and just keeps it nice and fresh. Yeah. So the coating applied during manufacture. Yeah, but every now and then we'll just get this special fluid, rub that onto the windscreen, and that just keeps it going.
Okay, thank you.
Okay with that?
Yeah.
Right. So we've looked at the windscreen wipers, and again you can see the wipers there, and that hydrophobic coating is going to assist the windscreen wipers. Bleed air blown up, a blast of air in front of the windscreen, and that's going to stop the rain actually getting to the windscreen. It's going to deflect it away. So again, we've got good forward vision. The other thing we can use is rain repellent. Yeah, and most aircraft have a rain repellent system. Yeah, the rain repellent is a chemical that we are going to spray up onto the windscreen, and again, we're going to use it in conjunction with the windscreen wipers. Yeah. What have we got with the rain repellent? We've got a reservoir, and that reservoir is pressurized. And the reason it's pressurized is to make sure that the repellent is forced down to the spray nozzles when we need it. Yeah, so you've always got a feed of repellent there. From there, little solenoid valve, yeah, and a delay unit built in with a solenoid valve. And the idea of that is the solenoid valve is your kind of on-off valve, and the delay unit is there to allow the system to reset once you've applied your first coating of rain repellent. Yeah, you've got a few seconds delay while the system primes itself, so the next time you select it, it's there and it's ready to squirt up onto the windscreen again. Yeah. So yeah, via the solenoid valve and the spray out over the windscreen. to help that spray, to make sure that it's distributed quite nice and evenly on the windscreen. There's a little bit of bleed air just behind the spray nozzle to help it to force it through. Yeah, and that spray nozzle will also it won't vaporize it, but it'll thin it out so you get a good spread when you apply your repellent. The rain repellent, yeah, as we saw earlier, there's a spray for each side. So left hand, right hand side. If let's just say we podge the left hand button there, pressing the left hand button is going to cause the repellent to flow down to the solenoid valve. It's going to be sitting there waiting. We press the button, solenoid valve will open and will allow raid repellent to go up to the nozzle. Because you've got bleed air at the nozzle, that bleed air is going to force the repellent onto the windscreen. Yeah, you put the required amount of repellent on. It's normally a measured amount that we get. Turn the windscreen wipers on, and the windscreen wipers will clear the rain away. Yeah, the delay valve is there to allow the system to reset itself. So the next time you press the button, you've got another metered shot of rain repellent squirted onto the windscreen. Next to your wipers, that one hasn't got the park position, but your wiper selector. The rain repellent needs to be used on a wet windscreen, so it's got to be raining. If you put it onto a dry windscreen, it gets very, very sticky, and it's a pain to get off. So it needs to be on a wet windscreen. Obviously, it's only as good as the area that the windscreen wipers are covering. So if I've sprayed my rain repellent on, yeah, a bit like on your car, the wipers are only going to cover a certain area of the windscreen. Yeah. So the area that's not swept by the windscreen, the repellent will just get carried away by the airflow. It'll just get washed away. It might foam a little bit, but that's nothing to worry about. Yeah. So again, yeah, just example. Yeah, you can your container. The reservoir is there to give you a metered amount of fluid. Yeah, podge the button. Yeah, that's going to allow the rain repellent. Yeah, it's up at the spray nozzle. Yeah, solenoid will open, and the repellent will then get sprayed onto the windscreen. The timer, once you've made your selection, the timer will hold the system off for, I think it's something like 5 seconds, so that the thing can prime itself again, ready for the next application. The actual circuit diagram, I'll put my hands up. I don't understand electrics particularly, so I'm not sure what's happening with this little lot. But I'm sure if you're interested, the B2s will tell you. However, we don't need to worry about it for our purposes. Again, just let me check, make sure I missed anything here. Rain repellent used anytime the rain intensity requires the use of wipers. Water contacts a clean glass screen, it spreads out wet in the glass. So the glass windshield treated with rain repellent, which causes the water to form into beads, so it can get swept away by the windscreen wipers. And obviously the airflow hitting the windscreen is going to blow them away as well, those larger droplets. There's a bit there that tells us what's in the system. Rain repellent applied by pressing the pilot or the co-pilot switch. solenoid operates a time delay circuit that allows 5 cc's of repellent to squirt onto the windshield. Release the switch. Yeah, solution hits the windshield, spread by the airstream and the water flow, and again, as we turn the wiper blades on, that will spread it about as well. Unwiped areas, you get a little bit of foaming from the fluid. We mentioned that. Wipers operated when the windshield's repellent's applied, just to make sure it's spread about properly. Don't apply rain repellent to a dry windscreen. If you do accidentally, then you need to wash it off. And I think that's pretty much covered rain repellent, the ins and outs of it. The maintenance side of things, yeah, what do we need to know about maintenance? Don't apply it on a dry windscreen. If you do, wash it off with soapy water, not soapy water, with fresh water. Your wiper blades, we talked about those, just checking the rubbers. Please make sure that we remember, if we're checking the windscreen wiper tension, it's done with a spring balance. Timer delay circuit in the repellent. Yeah. And that really, guys, is pretty much our rain protection. Has anybody got any questions on that? Rain protection?
Hello, Jim.
Yeah.
There is one line. Due to this foaming, the fluid forms on the window in the unwiped area for the short time after. However, the foam does not remain in the wiped area without the wiper operating. Due to this foaming, operating procedure will require that the windshield wipers be operating when the rain. In addition, the repellent is applied only one windshield at a time. So,
this
can
means,
you please?
This means is independent pilot and co-pilot, or independently we have to operate, right? Does this mean that?
Yeah. When we turn on the rain repellent system, it squirts up onto the windscreen, and the airstream hits it, and the airstream causes it to spread on the windscreen as well. Yeah. We've also got the wiper blades running, so the wiper blades are going to spread the rain repellent across the windscreen. However, on areas that aren't affected by the windscreen wipers, you might get this little foaming action. Yeah. The foaming is just the repellent that's not been spread about by the windscreen wipers. It says, due to the foaming, operating procedures require that windscreen wipers be operating when the rain repellent's applied. Yeah, and the rain repellent is applied to one windscreen at a time. Remember, I said that the pilot and the co-pilot's windscreen wipers were independent of each other. Remember I said that?
Yes.
Yeah. So with the rain repellent, the pilot and the co-pilot's windscreens, again, are independent of each other. So pilot podges button, and he gets rain repellent up on, that's his windscreen. Yeah. Windscreen wiper. Yeah. He presses the button and he gets the rain repellent squirted on his windscreen. The wipers are going, so the wipers are going to spread that rain repellent over the windscreen, so that the area that the wiper affects Yeah, it's going to be clear of rain. The areas that aren't affected, yeah, if it gets repellent on it, that repellent can foam a little bit. Yeah, it's a white bubble. It's a bit like the head on a beer. Yeah, because it's not being wiped away by the windscreen wipers. Yeah, it sort of sticks on the windscreen till the airflow takes it away. If for whatever reason we had a problem with the repellent on this side or the windscreen wipers on this side, yeah, if that repellent foamed and it wasn't being moved by the windscreen wiper, we'd just get foam all over and make visibility very difficult. So that's why you have the left hand and the right hand side, and likewise for the pilot and the co-pilot, you're going to have independent wipers. Does that answer your question?
Yes, Jim. Thank you.
That's all right. Just so long as I've explained what you need.
Hello, Mr. Jim.
Hello.
Sir, I have a one question, please. The line in the line in the notebook that the repellent can always be rejuvenated in the wipe area, but becomes ineffective in the unwiped area after approximately 35 applications. So can you clear me that after 35 application, after 35 application, it will not work, sir?
What's that saying is
the page number 64. Sir.
If we're flying and the area, the windscreen, the area that has the repellent squirted on it, yeah, we're just refreshing. When it says rejuvenated, we're talking about refreshing the rain repellent. Yeah, so we're just going to apply a bit more. We can always apply it in the wiped area. Yeah.
Okay, sir.
Becomes ineffective in the unwiped area after approximately 35 applications. Basically, the unwiped area, yeah, because it's not being spread about, yeah, it's not getting refreshed, so it becomes ineffective.
Okay,
yeah,
sir.
but that's only in the area that's not covered by the windscreen wipers.
Okay, sir.
Okay.
Okay, sir. Yes, sir.
Anybody else?
Is this the point to remember, Mr. Jim? Seems little bit important. It's a unique point to 35 after 35, because none of the sentence we have been focused like highlighted here.
If it was me, I wouldn't worry about 35 applications. No.
Okay. Jim, there's two other sentences I have noticed here. One is the rain repellent container pressurized to 85 pounds per square inch, and another is when switch is depressed, a solenoid operated valve controlled by a time delay circuit opens. This permits approximately 5 cc of repellent fluid to squirt onto the selected windshield. These 2 points, do we have to remember this?
No, don't think so. 5 cc, it's just telling you how much rain repellent's being put on there, so I wouldn't worry about that. And the fact that the system's pressurized, we don't need to know what pressure it's at, but we need to know why it's pressurized, and that's to make sure that the repellent is delivered to the windscreen. So okay. The actual figures, I've never seen a question on the figures.
Okay, Jim. Thank you.
Anyone else? Right. That's 3 o'clock my time. Does anybody want a 5-minute break before we carry on, or do you just want to carry straight on? I'll tell you what, we'll do this next little bit, and then we'll have a quick break before we look at the engine protection, and then that'll be it for the day. It won't take us long.
Okay, sir. Go ahead, sir.
Right. So what we're going to look at now then is the probes and the sensors on the aircraft. Obviously, the probes and the sensors are critical to the safe operation of the aeroplane. So we need to keep those protected. We need to prevent them from suffering the effects of ice and what have you. The sort of probes that we're looking at, pitot probes, angle of attack sensors, the total air temperature probes, static vents, and engine pressure ratio probes, to name but a few. They are all providing essential information to the aircraft computers and the aircraft instrumentation. Yeah, so we need to make sure that they're protected from the effects of ice from getting blocked up. So what we do is make sure that they are heated. Yeah, and they are heated continuously during flight. Generally, we turn power on to the aircraft, and the heaters will come on. Yeah, so as soon as we start the aircraft, the probe heaters start to kick in. Because they are critical items, if we get a failure in the heaters, we need to know about it. So we'll get a warning lamp illuminate to tell us that we've got a failure. Heaters in the probes are generally duplicated, so if we do get a failure in one heater, there's still another one there to keep us going. But again, we do get the warning. And as you're well aware, most of the probes are duplicated as well. And that duplication again is to give us safety and backup if we do get a failure in the system. Yeah. So your pitot probes, total air temperature probes, yeah, standby probes, angle of attack sensors, static ports, all got heaters, all there, all going to be protected. The probes themselves come in all sorts of different shapes and sizes. Obviously, depending on your type of aircraft, depends on the type of probe that you've got fitted. But the sketches or the slides just there to show not so much you guys, but the young upcoming engineers what these things look like when we're talking about them. pitot probes dotted about the aircraft all over the place, your inlet pressure probes, static vents, total air temperature probes, all serving, as I say, an essential purpose. And so it's vital that we prevent them from icing up, not so much on the ground, but certainly in flight. If we allowed these things to become contaminated with ice, we could jeopardise the safe flight of the aircraft. Air France 449. Yeah. Again, just showing us that we've got the heaters in there. Yeah, where we're going, I think most of the heaters, if I remember rightly, are run on 115 volt AC for the heating elements and the control of it. There's your DC, so all pretty much AC. Sorry, I'm just having to refer to the notes here because I want to make sure I've got the correct figures for you. So your pitot probes, 2 heating elements. We've said that. Yeah, 1 for each mast, 1 for each head. Supplied with a 115 volt AC, and we'll get a warning light if it trips off, if it fails. Yeah. On the ground, with at least 1 engine running, the pitot probes are automatically heated. Ground test switch allows us to check the heaters with the engines off. Angle of attack sensor, 115 volts. Again, ground test switch so we can check the heaters out. Total air temperature probe, 115 volt AC. The total air temperature probe works via the WOW switches. Probe, the TAT not heated on the ground, but it has got a test switch which allows us to check it. Static plates, again heated, and again there'll be a facility to check them. Fitted in the static lines. Obviously, we don't want water getting in there to create icing, so we put water traps in there as well as heaters. Don't worry about that. EPR probe located in the inside diameter of each engine nose cowl. Probes are heated by bleed air. So the EPR probe slightly different in as much as it uses engine bleed air to heat itself. As it's on the engine, it's near enough. It doesn't make any difference. Nice warm tapping for it. Air France, we talked about that earlier, yeah, where the pitot heads icing up, the heaters weren't good enough, the pitot heads iced up, and that was put down as a major contributory factor causing the loss of the aeroplane. There were other things that went on, but the icing of the pitot heads was a big concern. Masts on the aircraft, drain masts, yeah, the water waste drain. What they do is they put heater tape around the water lines, and that heater tape, it's just sticky tape with a little electrical wire running through it, and that wire heats up, yeah, and that prevents the water and the water drain from freezing. Yeah. Because those drains are external, if the drain froze, we'd get ice building up around the drain, and eventually that ice would crack off. As the ice cracks off, it could bounce down the fuselage, it could damage the structure of the aeroplane, and not only that, you'd have great big chunks of ice falling through the sky down to earth, and that wouldn't be nice for anybody that gets underneath it. Yeah, for your water waste line, it's just saying that on ground operations, yeah, supply changes to 28 volt DC to prevent overheating, and then via the WOW switches, it will kick into its 115 volt AC. So all the probes that we've talked about, apart from the EPR probe, running at 115 volts AC while we're flying. The heaters come on as soon as you've got one engine up and running, they'll automatically kick in. But there's a facility so we can check the heaters on the ground. Just remember to take the covers and blanks off before you turn the heaters on. Toilet drain, yeah, watch out for the toilet drain. That one does crop up now and then. And the toilet drain is heated at all times, on the ground, in the air. Yeah, using a 115 volt, again, heating element.
Jim.
Yeah.
Regarding this wastewater drain mass and the just before chapter we included the probe sensor and drain heating. The various supplies voltage mentioned here. Do you have to remember all these supply voltage for all these items?
No, as I say, they're all the same, aren't they? 115 volts AC. The only different one is the toilet panel. The toilet panel is continuously heated, but again, that's at 115 volts AC. Yeah.
Okay.
Yeah. So just remember that, and that covers just about everything.
Toilet panel is continuously heated with 115 voltage.
The toilet drain, yes.
Yeah.
Yeah.
Okay, thank you.
Okay.
Okay, thank you.
Anybody else? Right. What we'll do there, guys, we've just got a little bit on the engines to finish. So what I propose is we have a 10-minute break there. Stretch of the legs, stretch of the eyes, and then we'll wrap everything off with the engine side of things. Okay.
Okay, Ji.
Yeah, it won't take us too long. Don't worry about it. But I'm sure you guys need a break as much as I do. So 10 minutes. Turn.
Okay.
Okay, take your time.
Thank.
Yeah.
Excuse me, Jean.
Yeah.
Are you free?
Yes.
And I want to ask one question that we are doing this ice protection and anti-icing and de-icing. And in this chapter, we are learning from your side, not from the book side. So we don't go line by line. At the examination point of view, how can we go for the study and pass the exam?
Well, the only way you're going to pass the exam is by reading the notes.
Yeah.
I'm sorry. There's nothing else I can do. There's no shortcut to it. You have to read the material. Yeah. All I can do is show you the material, explain what's going on, but I can't tell you what's coming up in the exam because I've got no idea. Yeah. The questions that I send you, are there to help with the revision. So you're looking at the right areas. Yeah, but just look at the level of the question and think, well, what as you look at each page, just sort of think, well, what question could they ask me from here? There's not a lot else I can say, Navin. It's just a hard slog. You have to read the material. We can't just we can't just say, oh well, this is going to be a question, this is going to be a question, this is going to be a question, because we genuinely don't know what's going to come up. That's from the exams department.
Yeah, I understand it, but when we have to go thoroughly to the notes, and we have to memorize it. That's the final.
Not memorize it, but I mean, you're working on aircraft anyway, aren't you?
Yeah.
Yeah. So a lot of the stuff you'll have a good background knowledge of. So what you do, you're not memorizing the notes, but you're looking at the content. Yeah. So you understand what it's saying to you. So when it does come to the exam, yeah, you'll think, oh well, windscreen wipers. Yeah, we talked about windscreen wipers. Why do we have them? Yeah, to clear the rain away. What could be a problem with a windscreen wiper? Oh well, they lift off the windscreen, so we need an extra system to help them. So you're not memorizing each word, each sentence, but you're memorizing the idea behind the system. Yeah, so you've got an understanding of it. So when there's a question comes along, yeah, you've got a good idea of what you're talking about. You understand what the question's asking you, so you can answer it.
Okay, thank you.
Yeah, I can't help you any more than that, because as far as the questions go, you know as well as I do what the question's going to be. I've got no idea.
And one thing I want to ask: can we get the previous questions which are asked before in the examinations?
No, all those are held by the exams office, and as I say, we don't see them. But those questions, they can get reused. So if you do an exam in Nepal for Module 11, that question might get used again in Pakistan for Module 11. So all the questions are kept secret with the exams people. Yeah, all we can do is say, well, like I said before, oh well, I've seen a question to do with that before, so make sure that you know about that bit. Yeah, so as I'm going through and I see something I recognise, then I'm letting you know. But obviously, I can't say every little thing because I just don't know.
I understand that, but I want to know that the question asked past years before. 2-3 years, and or when we can have that module so that we can have the one reference to study, and we know the level of questions also, so that we can study in that way. So we want that.
Well, like I say, we don't do that. Yeah, the questions are held by the exams office, and they don't let anybody else see them. Those questions are only used for exams, and the old questions they just dispose of, and that's one of the reasons now that we're not allowed to use multi-choice questions anymore. It's all got to be open questions, and that's come from IASA.
And how long the questions are changed? Means every year the questions are all changed, or it keeps on repeating?
They'll keep on repeating. Not all the same questions. There are different papers. So you might get a question that appears in paper number 1, and it might appear in paper number 3, but we don't know which papers they go into. You know, so that they're in use a lot of the time, but you know, we don't know what's coming when.
Okay.
I think we will be puzzled because in other examination we will find sample model questions, so that not the real but sample, and then that will be the reference to the exam point of view. So that because everyone are new, so everyone is confused of the level of questions answer, because every time my friends are asking which type of level questions come, this question will come or not, this data is not
right. Well, I can't tell you about the questions. I've explained that, but what I've done, I've sent you a list out of how many questions from each area, and I've sent what level those questions are going to be. You know, so you could look at ice protection. You could look how many questions are there going to be. There's going to be, I don't know, 3 questions. What level are those questions going to be? Oh, so there'll be 3 questions at level 2. Yeah, so you've got that information. You've already been given that.
Yeah, we have got that information. I know, but not me, but everyone is confused in this, because everyone is giving this exam first time. So I think because when we get some sample model from any site, because this one is not the real one, because you will also not get the questions. We will also not be before exam, but the level of questions and answerings, and the sample level, so that we will be reference for that, and we can go thoroughly to the book, so that we can have easy for the exam. Can we get any sample question from any places, not from you, if you have any idea also on that, from internet and other sites?
Well, there's lots of sites about, but the questions that you will get will only come from our notes. Yeah, so you can use other sites. You can use the internet for practice questions. Yeah, but just be aware that the only questions will come from our notes. Yeah, so make sure that when you look at these sites, when you look at the questions, read them with our notes to make sure that you get the right answer. Do you see what I mean?
Yeah, I understand that.
You did.
I'll have a look through the internet tonight. If I get time, I'll have a look and see if I can find any particularly good sites. But I tend not to use them, because it's all right. It's all right going for the questions, but at the end of the day, guys, we're training you to be professional, licensed aircraft engineers. We're not training you to pass the exam. Well, you've got to pass the exam, but you need to understand the aircraft systems. You need to understand how they're working, because at the end of the day, you are going to be licensed. You are going to be carrying people's lives on the back of your work. So if you just train yourself to answer a couple of questions, yeah, and you don't understand the systems, you're not going to be a very good engineer, and people may well die as a result of that. So the whole purpose of you doing this course is so that you can understand the systems, understand the background to the systems, and then you're going to prove that knowledge by the exam. Do you see what I mean? You know, I could teach anybody to answer that question, answer that question, answer that question, but if they don't understand what they're answering, then it's a pointless exercise. Yeah, and that's the whole purpose of us doing these courses, is so that you become better engineers. You understand what the aircraft systems are doing. So if you get problems, you're not just guessing at it. You're actually going out with the knowledge of how to repair that aircraft and how to operate that aircraft safely.
Yeah, then you are right. But at that time we have a AMM, no reference.
Yes, you will. But if you don't understand the system, the AMM's just a lot of words, isn't it? You need that background understanding so you can understand what the AMM's telling you.
Yeah.
Do you see what I mean?
You are correct. Yeah, Jim.
Yeah. You know, don't take this the wrong way, please.
No.
But Nepal, in the olden days, had an awful safety record, and nobody wanted to know. But Nepal aviation now is really improving, and it's guys like yourselves that are bringing that standard up, and it's guys like yourselves that are going to see Nepal Airlines be allowed back into European airspace, because you are the people that are putting the effort in. You are the guys that are showing the aptitude, the intelligence, the enthusiasm to carry the aviation in your country forward. And it's showing. Yeah, it really is showing. That people passing the exams, people getting the licenses. Yeah, there's a lot more confidence in Nepali engineering, and it's because of you guys that's happening. So, you know, don't let yourselves down. Keep going with the hard work. Prove that you're good engineers, and prove to everybody else, yeah, this is what we can do. And that's the whole purpose of us coming to you, or, well, because of COVID, doing it this way, but that's the whole purpose of us coming out, training, doing the lessons, and the whole purpose of you passing the exams. And with that bit of hard work, I've got no doubt whatsoever you will. Yeah, from the guys I've trained before out there, from the guys I met the last time I was out, the back end of 2018, I think, doing aerodynamics and human factors. Yeah, and the exam results were really good. And likewise, you know, you've done your module 17 the other week. I don't know what the results are, but I've got no doubt that they'll be good. And the guys that have gone before you have had good results. So don't freak yourselves out. You know this stuff and you are good enough. Yeah, just have that confidence in yourselves, because you guys are good, and you are the future, and you are showing the rest of the world how good the Nepalese engineering can be. Lecture over. Right. Has anybody got any? Now that I've finished banging my gums together, anybody got any questions on anything else so far?
No. Yes, sir. Yes. Can you re-explain the testing procedure, heating testing procedure on ground of all these pitot probe, angle of attack, and total air temperature probe?
Well, there's nothing really to explain. Each aircraft has got these probes fitted, every different type of aircraft. All we're going to do with the aircraft is check that the heaters work, and there will be a procedure in the AMM that you need to follow just to check that the heaters are operating correctly. Yeah. So that's all there is to it. The important thing when you're doing the heater checks is to make sure that you've taken all the covers off, so when the heaters are turned on, they don't melt the cover. Does that answer your question?
Yes, this is the simplest procedure, but in the textbook we find some few lines regarding each and every props a ground testing procedure. So I'm a bit confused.
Yeah, don't worry about that because it's and that's what I'm saying. That's going to be peculiar to the type of aircraft, isn't it? So what we're doing when we're testing, we're just making sure that everything's working. Because it's going to be slightly different on each aircraft. The general procedure will be to take the covers off, yeah, turn the heaters on, check that the heater is operating correctly, turn the heater off, disconnect power, wait till the heater's cooled down, and then replace the cover. That's going to be the general procedure for every aircraft. The specific procedures, yeah, are going to be type specific. So the procedure for checking the heaters on a jet stream is going to be different to checking the heaters on the ATR. But so long as you know that they need to be checked and how do I check them without causing any damage, that's as far as we need to go, really.
Okay. Thank you so much. Yeah.
I'm just trying to find the page you're on about.
Page 69.
Yeah, you're looking at testing the windscreen, yeah?
No, sir. Ground testing the pitot switch, pitot prop, angle of attack, and total air temperature prop.
Page 69?
Yeah, the material we have, it is in page 69. Prop sensors and drain heatings.
We are having old book, so it might be other page number for you. But it's chapter 9, probe sensor and drain heating.
Chapter 9, section 1.
Yes.
It's in page 83.
Yeah.
'83 is the oldest book, and second revision is on 63. I don't know which page with Mr. Jim.
No, right?
Mr. Jim has 2020.
20 April, yeah.
Yeah.
It's the same topic just before.
Yeah, no, I can't see that in my copy. But no, the testing, just know why we do it. We don't need to know the step by step. Yeah, I'll have a look later and I'll see if I can find it. I can't find it at the moment.
It's the same, Jim, that some of the pilots are need power supply in flight 115 volt AC and some on ground 28.
On chapter 9, you can check chapter 9.
No, I haven't got that in mind. Leave that one with me. I'll get back to you on that one.
Okay.
Yeah, but don't worry about the testing of it.
Okay, sir. Okay, thank you so much.
Yeah, don't worry about that. Just know that all apart from the what did we say, the EPR probe, which sits in the engine, yeah, everything else has got a heater in that runs at 115 volts. Yeah, the toilet drain is the one that's on constantly on the ground in the air.
Yeah.
Okay.
Okay, Jim.
Okay, sir. Okay.
Okay, lovely. Right, the last little bit then that we need to look at is engine ice protection. Yeah. Depending on the type of aircraft, depends on the type of protection that we're going to give it. Obviously, we don't want the engines icing up. Yeah, so we need to make sure that the engines and the probes in the engines are sufficiently protected. The two basic types of engine protection for turboprop aircraft, we normally use the electric heating, the electric mats. Turbojet normally use thermal icing, which is ducting hot air around. Yeah, so your turboprop, we might use a bit of thermal. Generally, it's electric. Your turbojet, your turbine engines, is going to be thermal because we've got plenty of hot air around to use. Yeah. Sometimes because the engine is using oil for lubrication, that oil's circulating, that oil gets hot. So we can use the heat from that oil again as an anti-icing measure if we need to. If we allowed ice to form in the engines, get to the engines, if we didn't have that protection, obviously there's the potential for a lot of damage. More so if the engine is left unblanked overnight. You get heavy rain. If you get rain sitting in the intake, if that water starts to freeze, start the engine up. There's a big pressure drop at the front of the engine. The water that's in there will freeze instantly, and once it's frozen, once it's ice, if it hits the engine, it's going to do untold damage. So we need to make sure that we've got that level of protection. Yeah. Certainly in the air, very cold at altitude. Yeah, the engines are operating, so we need to make sure that they're kept efficient and that the heating system is working. So your engine anti-icing, like we said, depends on the type of aircraft. But for your big jet aeroplanes, turbine aeroplanes, all we're going to do is take a tapping of bleed air from the engine, from one of the compressor stages, run that through a pressure regulator and a shut-off valve. Pardon me, basically your shut-off valve is your on-off valve. Yeah, and that hot air is then going to be ducted around the nose of the engine cowling. Remember we talked earlier about the piccolo tube, the spray tube. Yeah, and that's exactly the same thing. It's just a tube that runs around the inside the nose of the engine cowling, and inside that tube there's a lot of little perforations, and we're just going to blow hot air into the nose cowling just to keep everything ice free. Yeah. Safety devices, there's a couple of pressure switches in there just to make sure you can see that the system's working. Relief valve, if we get too much pressure, we need to relieve that, so we'll stick a relief valve in the system. Low pressure switch is going to tell us if we've not got enough air going through. High pressure switch is going to tell us if we've got too much. Little probe in there. Again, we can take a tapping of hot air, as we said, with that total temperature probe, not total temperature, the pressure ratio tube. Yeah, and we can just run a little bit of hot air around that and keep that free from the effects of ice. Yeah. System switched on. Yeah. Make sure it's working, and away we go. Again, that's an example of the piccolo tube. Yeah, you bleed air coming through, and that bleed air being fed through that perforated tube through the nose cowl and sprayed onto the leading edge of the engine intake. Yeah, regulating valve to make sure we don't get too much pressure, and we've got an exhaust vent to duct away the excess air once it's done its job. Yeah, again, just the front of the engine. Yeah.
Can you go back to the back slide?
That one?
No, the back. One more back. The diffuser slot, mainly I want to ask about the diffuser slot. In the back slide, not this.
Not sure where you're looking. Diffuser slot.
No. Yeah, this one, the diffuser slot. So what is this about?
That's just letting the excess air out. Yeah, where the diffuser is. What we're doing, we're filling up the nose of the engine cowling with hot air. Yeah, we need to make sure that doesn't overpressurize. So all it is the hot air. Well, once we used it, it's just allowed to escape. Yeah, so that's just an escape path for the air once it's used.
So it's a kind of exhaust like then.
Yeah, like a bit like that.
Okay.
Yeah. So there'll be a couple of those dotted around. Yeah. So once the air's warmed through, can you see in there if that's your the nose cowling? Yeah. So that air's been sprayed around the leading edge. It's got to go somewhere, so it go into the nose cowling. Yeah, so we've got to let it escape, and it'll go out through those exhaust slots or diffuser slots, as you just called them.
Okay.
Yeah.
Yes, sir.
Yeah, and this one they've actually provided a pipe. So rather than letting the air dissipate naturally, they've actually provided an exhaust pipe for the air. So just the same sort of setup, but slightly different. Yeah, the hot air coming in through the piccolo tube. Yeah, heating the nose up, and then just being ducted away to atmosphere. So we're not getting a big buildup of pressure. One of the things that it does mention on the front of the engine, on the what they call the bloody thing. The nose cone, that's what I'm looking at. Couldn't for the life of me remember the name of it. On the nose cone in the front of the engine. Yeah, that's susceptible to icing as well. So what they do is they glue a little rubber cap on the front of the nose cone, and that little rubber cap is slightly offset. So as the nose cone's rotating, this little rubber cap is vibrating, and because it's vibrating, it's not allowing any ice to form. And that, dear heart, is in here. Yeah, it's under control and indication in my notes for the engine anti-icing, about halfway down the page. Large high bypass engines may not use thermal anti-icing for the nose cone. Engines may have a small cone of soft rubber mounted slightly offset on the front. Yeah, and again, when you find that bit, that's worth sticking a highlighter through there. The high bypass engines, rather than ducting hot air around the nose cone, all they're going to do is stick this little rubber cap on the end, and the little rubber cap's gonna vibrate because it's offset, and that's going to stop ice forming. Again, your your anti-ice control panel. We looked at that previously. Your heaters, yeah, static heaters, test switch for them, wing anti-icing, and on here we've got the engine anti-icing. Yeah, thermal system. Yeah, you know that because you got your wing. Yeah, your thermal system. And again, if we get a failure in the system for whatever reason, we're going to get a warning light telling us that the anti-icing system's inoperative. Everybody okay with that? Excellent.
Yes,
right, the other type of protection that we'll come across is the heater mats. We've already discussed heater mats, and on your turboprop engines, heater mats are commonly used around the front of the intakes. Again, they're split up into sections. Some of the sections are permanently heated, continuously heated. Other sections are intermittently heated. The extreme leading edge of the intake and the little breaker strips are normally the continuously heated areas. The other areas heated intermittently, and that just ensures that we're not soaking up too much power. And by having small sections, ice that breaks off, it's only going to be small bits of ice. It's not going to cause any damage as it's accompanied with the aeroplane. Yeah, again, I'm just double checking I've not missed anything here.
Jim.
Yeah.
In the previous chapter, sorry, this same topic we covered recently, that they mention certain temperature range. Normally, engine intake icing can be expected at a temperature of +8 degree to 10 degree with visible moisture present. These data, do we have to remember this? You highlighted earlier.
No, if you remember that at the intake, you can get icing at ambient temperatures above freezing. Because where your intake is, when the air goes in, you're getting a big pressure drop, and that's causing a big drop in temperature. So where you've got high ambient temperatures, it's still possible to get icing at the intake.
Mm-hmm.
Yeah.
Okay. So this data don't need to remember, right?
Not the figures, no.
Okay, thank you.
Yeah, so your different areas constantly heated, intermittently heated, and between the various areas, certainly on your propeller aircraft, what we can do is vary the amount of time heat's being applied. Yeah, we can have a fast cycling speed or a slow cycling speed, and it depends on the icing conditions that we've got, whether we want to cycle everything quickly or whether we want to cycle it slowly. Fast cycle, a high temperature range when water content is larger. Slow cycle at low temperatures. Yeah, and again, that's just to give us that protection, to make sure that ice isn't going to build up. Yeah, so the fast cycling, slow cycling. Yeah, slow cycle, low temperature, less moisture in the air. The fast cycle, higher temperatures, more moisture in the air. So your fast cycle, slow cycle, just depends on the conditions as to which you're going to use, but they're both fulfilling the same function. They are both preventing the ice formation. That again, just taken from the notes, just an example of an ICAS panel, just showing the the various elements. Yeah, you're icing what your duct pressures are, what your temperatures are, that sort of thing. Just let me have a quick look here. Electrical systems, switched on from a control panel in the cabin. We've already said that. System, for your electrical system, turn the system on. System will stop operating if we turn it off. If the total air temperature is above 7 degrees, because you're not going to get ice in there. Once your propeller RPM is below 600, that means that the thing's winding down, so it'll turn off. Or if we get a failure in the system. If we get a fault, we'll get a caption, we'll get a light telling us. And that, guys, was ice protection. So we've got through that quite nicely. The rest of it goes on to fire protection. We're not going to do that today. We'll do that, I think it's on Monday. Monday or Tuesday we do fire protection. So ice protection, nice steady plod there. Has anybody got any questions whatsoever on ice protection?
Can you go back one slide? That's fast cycle and slow cycle. Yeah, it's when we're looking at the electrical heating. We've got that electrical heating going on, and we can either run it so it's going on, off, on, off, on, off, or we can run it so it's going on, off, on, off. So you've got a slow cycle where you've got low temperatures, but you haven't got as much moisture in the air. We've got a fast cycle where you've got higher temperatures, but you've got more moisture. More moisture, more potential for icing. Okay, good. Thank you.
Jim?
Yep.
In the ice formation, it is mentioned when ice will only form on an aircraft when it is flying in cloud or precipitation, where the water droplets are super cool. So in the precipitation, what we will consider then?
Precipitation just means rain. It's just a posh word for rain. So if you're flying in clouds that contain rain, contain water, that water can stay in its liquid form at temperatures down to way below zero. I think -10's the figure for the run-back icing. As soon as that water is disturbed by something moving it, jolting it, it will turn to ice. And as it turns to ice, that's when it forms on the skin of the aeroplane. Does everybody have access to YouTube?
Yes, sir, we have.
You've got YouTube, right? As soon as though we're a couple of minutes early, if you get the chance, either this evening or tomorrow morning, go onto YouTube and just type in supercooled water. And there's a couple of, they only take about 20 seconds. There's a couple of good little videos that show you what supercooling is. Where they get a bottle of water, they put it in the freezer, the water will remain as a liquid, and as soon as you start pouring it, it turns to ice. So if you get the chance, have a look at that. It just explains what supercooling is. That's what I was saying. I did have the video clip, but I couldn't get it to run for some reason. If nobody else has got any questions, then we'll call it a day there, and we'll regroup tomorrow for fuel. If it's all right with you, Yadav, I'll send you you the questions again for distributing?
Okay, no problem.
That would be wonderful. And you got me message to apologise to your wife. I didn't mean to embarrass her yesterday.
No problem at all.
Yeah. So long as I didn't cause her any offence, that's the main thing.
Not.
Jim.
Yeah.
Jim.
Hello.
In very short way, can you please again explain the difference between mixed ice and rime ice?
Yes. Mixed. You're talking about rime ice, yeah?
Mixed ice, that is glime and rime.
Yeah. What happens with that? It's as the name suggests, it's a mixture. When it strikes the leading edge of the wing, yeah, it's in its liquid form. It strikes the wing. It gives off that latent heat, and it starts to run back, just as run back icing or glaze icing does.
Yes.
But because it's running back at a slower rate, yeah, it gets bits of air trapped in it. So it becomes, although it's moving back, it's got the air trapped in it to give it this milky appearance. With the rime ice, the individual droplets are freezing on contact. Yeah, so they're not giving away that heat. They are just freezing as soon as they hit the skin of the aeroplane. And obviously, each individual ice particle then joins up, and you get this really, really white, and it's very lumpy and bumpy type ice formation.
Okay, Jim. Thank you, Jim.
My pleasure. Anybody else got any questions before we finish?
Sir, we will study again and tomorrow we'll ask.
Okay, that's absolutely fantastic, and I'll get these questions out to Yadav probably in the morning now. And tomorrow, I think we are going to have a look at fuel systems. And again, fuel systems are fairly simple. There's not a lot to worry about there. Yeah. Right. Thank you very much indeed for your time and your company today. I hope everything's been all right. If it isn't, I'm sure you'll let me know. But if not, enjoy the what's left of your evening.
We'll have a dinner and sleep, sir. Good night.
Good night and enjoy your sleep.
Thank you so much, Jim.
Yes, sir.
Thank you. Good night.
Okay, good night.
See you tomorrow, Jim.
Good night.
See you tomorrow. Good night.
Good night.
Good night.
Time to unbox your beer now.
Yeah. I've got to take the dog for a walk first. And it's going to snow.
All right, Jim. Good night.
All right. Good night. Thanks again.
Good night.
Good night.
Good night, Jim.
Good night. Thank you.
दिगम्बर सर
दिगम्बर जी त के हो यार, कहाँ हरायो?
त्यही त खै बोल्दैन यसले क्वेसन दिनेवाला छैन यो जति जे सोधे पनि होइन।
म त अब विकास जी तपाईँको कोही छ पाकिस्तानतिर कि के हो, कतिचोटि रिपिट हुन्छ भनेर सोधिराख्नु भएको थियो।
होइन मैले रिपिट हुन्छ भने जाउँला नि पाकिस्तान, के भएर हामीलाई जसरी भए नि पास हुनु छ, बरु पाकिस्तान गएर क्वेसन लिएर आउने।
यसले जति नै गुड नाइट भने पनि यसले दिनेवाला छैन क्या।
त्यही त अघि त यत्रो नवीन दाइले सोध्नु भएको, यसले फेरि यो इन्जिनियर यो त्यो नेपाल एभिएसन कहाँ युरोप सिरोप कहाँ पुर्याइसक्यो हाम्रो कुरालाई। ठिकै छ, अब केही नदिने के गर्ने, यस्तो छ क्या अब यसले पढाउन एकदम सजिलो पढाउँछ, यो जुन स्लाइडहरू पढाउँछ नि। हेलो
हजुर सुनिरहेको छु।
यसले पढाएको चाहिँ एकदम सजिलै लाग्छ, यो फटाफट स्लाइडहरू पढाउँछ, तर यी क्वेसनहरू यति साह्रो लेभलको आउँदैन कि। अनि त्यसले गर्दा अब यसो के गर्ने, हामीलाई त पास हुनु छ नि यार, त्यो इन्जिनियर त बनाउला नि लाइफ टाइम म्यानुअल पढ्दै पढ्ने हो नि। कि पाकिस्तान जाने
त्यही त पाकिस्तानै जानु पर्ने हो कि के हो।
के गर्ने यसले फेरि एउटा के भनेर उ गर्छ, यसले दिँदैन कि। अनि हाम्रो अरू यो मोड्युल 15-17हरूमा दिएछ कि छैन?
त्यो छैन, क्लासमा तर रिभिजन गराएको थियो, सोधेको थियो होइन।
अनि त्यसबाट कतिको आयो एक्जाममा?
आउन त आएन होइन, तर पढाइमा बुझियो क्या, रिलेटेड थियो।
ए अब यसको कस्तो छ नि, अब त्यो मैले एउटा क्वेसन हेरेको, अब यो सुपर कुलहरू छ नि त्यसमै छ कि यस्तो कन्फ्युजन छ। अब त्यो अबोभ 0 डिग्री सेल्सियस, बिलो 0 डिग्री सेल्सियस, सुपर कुल, अब यस्तो भन्छ, अब त्यो त सबै रट्नु पर्यो नि त, त्यो अब हो कि बिलो। फेरि यसले भन्छ फिगर्स इज नट इम्पोर्टेन्ट, यु डोन्ट हेभ टु रिमेम्बर द फिगर।
हो नि,
के हो यार दिगम्बरजी, तपाईँ कहाँ हराउनुहुन्छ यार?
भर्खर खाना खाएर आएको के।
अनि अहिले खाना खाएर के काम, अब त क्लासै सकिसक्यो।
त्यही त सकेर अनि गएको थिएँ कि उता।
ए दिगम्बरलाई खानै, अब पाकिस्तान जानु पर्यो दिगम्बर।
किन?
यहाँ यो नेटले के अरे यो एएसटीले जुन पाकिस्तानमा क्वेसन दिन्छ नि, त्यही क्वेसन तपाईँको साथी छैन एउटा पाकिस्तानमा?
छ।
त्यसलाई फोन गरेर
अब त्यहाँबाट मगाउनु पर्यो क्वेसन्सहरू।
त्यही क्वेसन यहाँ आउँछ। नत्र म खगेन्द्र तपाईँ तीनैजना प्लेनमा गएर हिमालयमा गएर पाकिस्तान चार्टर गरेर क्वेसन लिएर आउनु पर्यो।
यो गयो कि गएन, जिम छँदैछ कि क्या हो? सब सुनेर बस्छ फेरि यसले।
छैन। बाँकी को छन्? म छु, तपाईँ भयो, यो कृष्ण विश्रेष्ठ।
अब हामी पनि लिभ गरौँ न त।
हजुर
हुन्छ ल। हेलो ल, गुड नाइट।
ल गुड नाइट।
गुड नाइट।